take a look here at the schedule classes. So we started the diffraction yesterday, right? Diffraction. Let's put it like that. We had the physical pendulum experiment yesterday, and we will continue with diffraction today. And don't forget, tomorrow is the exam number 2. See notes for specific sections of the chapter, right? Lab 1 do. Let me abbreviate here diffraction. Lab 1 do tomorrow, and exam 2 tomorrow as well. Partial exams are from 12 noon to 2 p.m. Final exam is going to be from 8 a.m. to 10 a.m. Okay, so let's go back to our notes and review our results for the diffraction, because we are going to need that. It's very difficult to memorize this equation, right? Too much stuff in there. Result for diffraction. Intensity. Intensity of the light due to diffraction, right? This is a very good model that we have here. It's very difficult to memorize it, but there is a simpler way to rewrite that. Instead of writing all this whole thing that you see here, just write that as alpha, right? And alpha upstairs and alpha downstairs, where alpha is equal to this expression here. And just to remind you, where A is the size of the slit, comma, lambda is the wavelength of light, and theta is the angle from the central maximum. Now makes easier to understand this equation, right? Becomes easier to understand this equation. Whenever alpha is equal to 0, this ratio goes to 1. Okay, and let's plot it just to see how it looks like. Every semester I do that. I use Excel. Very useful tool. I think this is better than calculators. View. Right here. Freeze panes. Okay. Alpha. Alpha in degrees. Alpha in radians. Intensity. I'll normalize the intensity, okay? I'm going to write that down, I over I naught. So there is no unit there to worry about, or unknown values. Oh, good. Alpha. Instead of font, superscript, like that. More students coming in. And what we end up getting here, let's start with alpha. Now we're not going to start at 0.1, right? Let's put 0.1 degrees. And then we have to, no, you know what? Let's start with 0.5. Otherwise, it's going to be too much radians. And the intensity divided by intensity square is going to be sine of alpha divided by alpha. All of that is raised to the first power. Okay, the next one should be 1 degree. Every 0.5 degrees. Oh, by the way, I have to do the negative as well, right? Well, I'll do afterwards. Let's go to all the way up to 45 degrees. You don't need more than that. And this is an even function because of the square here. So we know that at negative alpha is going to be the function is going to be the mirror image of its positive value. Okay, so we have a very flat, very flat relation here. So let's extend all the way up to the largest angle that we can do is 180. Well, I would say 90. It's not 180, but 90. Okay, that's the largest angle that we can make it. 180 wouldn't work. 90, right here. There's a very simple way to realize that, right? So six. Okay, the screen. Okay, the screen is right in here. Okay, that's half. That's gonna be half of the screen. You start with small angles here, 0 degrees, and the further you go, the closer you get to 90 degrees, right? 90 degrees is the limit. If you go beyond 90 degrees, then the diffraction pattern would be behind you. That doesn't apply because we have a screen, and if the screen is infinitely long, the largest angle that you're gonna get is going to be 90 degrees. That's why we're going just to 90 degrees. And let's take a look at our graph again. We plotted only up to the, plot from scratch again. This one and this one, insert. Okay, so what we have here is the case of a very small slit. That's what we have here. The case of a very small slit. That's why we have a very flat a very flat curve. So now let's elaborate a little bit more on this intensity. Instead of using the simplified equation, right? Let's use the full equation. Let's use the full equation. And then we vary the parameters according to what we can get in real life. So alpha is going to be equal to what? Let's write that down here. Alpha. Let me see if I plot. Oh, wait a minute. I made a mistake here, right? Nobody picked up that mistake. I plotted against degrees, right? I was supposed to plot it against radians. Let's see if we get a better. Yeah, we don't get anything different. Yeah, no different. So it doesn't matter at the radians or alpha or degrees. To get the same plot. The only difference is what goes in the x-axis, right? So there was no mistake there in the first place. Let's see. What this thing is not dragging, unfortunately. But let's get our alpha here. Our equation for alpha. Going back to the solution. Notes. Alpha is pi a sine of theta lambda. Pi a sine of theta. Okay, but now I'm going to do the following. Instead of writing it as alpha, I'm going to write this one as theta, okay? Just to save some of the work. Pi alpha divided by lambda. Lambda I'm going to put in G2 now. And I'm going to replace here with theta. And that should be theta in degrees as well. And that's the alpha that we want. And I'm going, by the way, I'm going to put it in writing here. And now I need to fill up the values for F2 and G2. F2, by the way, is going to be A. And I'm going to put it in meters. Lambda, yeah, it's going to be in meters as well. Like that. The F2 and the E2 and F2 must have a dollar sign here because they are going to be constant. The only thing that's there is the angle theta. Let's play with this guy here. I'm going to put 1 micron. That's a reasonable value. And I'm going to use 600 nanometers, which is red wavelengths. And now we can start calculating that. Okay, and he didn't calculate that. Why is that? Let's see what's going on here. Pi, oh, pi is the pi. Ah, I'm mixing up. Pi is written like that. Okay, now I got it. Watch out for those things, right? And that's the real alpha now. That's the real alpha. And if I'm going to write down my intensity, I have to write that in terms of the real alpha. And 1 micron, 600 nanometers. 600 nanometers is 600 nanometers is what? 600 nanometers is red light, right? And let's see. Good. Okay, so I have to update everything here to get, now look what's happening. That now that I'm using the actual equation, the first equation that we used was just to have a rough idea what how the function behaves and if I had the, typed it correctly. But now that I'm using real life values, for A and lambda and theta, I start to see a sharper value of the intensity. All the way down to 90 degrees. Right here. Okay, and okay. That's what we get. First maximum, right? The bright maximum. That occur at theta equal to 0. I'm gonna put theta equal to 0 here, but I'm not going to type an actual formula. The alpha is going to be 0 as well, but the I over I naught is going to be equal to 1. Excel don't like to divide 0 by 0, okay? If I were to make this cell divide 0 by 0, it's going to give you this funny value. So we have to tell Excel that 0 divided by 0 is 1 for this specific case, not all the time. And now we can start playing with those values, okay? Instead of 1 micron, let us make it larger. Let's make it 10 to minus 5, 10 microns. And let's see what happens to this function. Oh man, I increased it too much. Do you see the big difference? I'm gonna undo it. See, it's a big difference, right? So I increased the size of the slit too much. Okay, instead of doing 1 micron, instead of doing 10 microns, let's do 2 microns, so you can see, okay, the evolution more clearly, right? I'm going to undo so you can compare it and redo, undo and redo. Do you see that the diffraction peak, the intensity becomes sharper and sharper? Okay, undo, redo, undo. Okay, at this point here, in which the slit size is comparable to the wavelengths, we have this broad spread out of the intensity, and we even have our minimum, just a single minimum right in here. And I want to put that here. It goes 0 degrees. Yeah, let's put in degrees, right? And look here, there's a little peak here. That's what we get for those values here of 1 micron and 600 nanometers. And if we redo it for 2 nanometers, okay, we gotta do by hand, 2. That's what we get. Just like playing a movie, right? I'm gonna make it 3 nanometers. Yeah. And we start to see some little smaller rises in the intensity, but it's very small compared to this one. This one has a value of 1, right? But what about this one? This first peak here, next to the other one, has a value of 0.04. It's less than 5% of the maximum bright. And then we can go to 4 micrometers. We can go to 5 micrometers. We can go to 6 micrometers. Notice that the maximum is becoming sharper and sharper, the central maximum. We are creating this diffraction region here as well. That is still 5%, less than 5% of the central maximum is 4.6% if you look at the values here. And that is at 8.5 radians. 8.5 radians is around 15 degrees. If you're going to see 8.5 radians, yeah, see, it's around 15 degrees, a little bit more than 15 degrees. And we're going, we're moving towards regions of macroscopic objects, okay? It's easier to make 7 microns of, it's easier to make a slit of 8 microns of diameter, and so on, right? 9 microns. It comes to a point, you're going to have very little data points here in this region of maximum brightness, okay? Then you have to do something else. 11 microns. Let's see how large this one is right now. It's still 4.7%. This peak here is still 4.7%, so it's negligible. 0.047. And now let's go to 20. Yeah, okay. And now we are running out of data points here in this region. What do we have to do? We have to increase the density of the values between 0 and the other one. So instead of going from 0 to 0.5, let's go from 0 to 0.1, right? And then we are going to, okay, now you have a higher resolution in your graph, right? I increased the population of points by 5-fold. So you can see more data there. And keep on going. We are 5 degrees, almost 6. Let's see here. Okay. And I'm going to decrease the size of the marker right in here. Okay, I'm gonna make it very small. Not doing anything. Solid. You see here. Okay, that's the color. That's the fill. One more student coming in. We're in marker options. Okay, size. That's what I want. Okay. Okay, so you're making those data points smaller and smaller. Oh, now you can start seeing the diffraction, the little diffraction peaks that we have here in this graph, right? Sharper. And now the maximum intensity of this first diffraction peak is 4% only, 0.04. 1 to 0.039, which is almost 4%. And then we can start seeing the other ones as well. So what you're seeing here is that light is starting to behave as a ray, as a particle. Okay, that's what you see. Particles don't manage to spread out over a screen. Only a wave is capable of doing that, right? As I increase the size of my aperture, the intensity is spread out over a smaller angle. In this case, the angle is only 1.8 degrees. I'm reading here. The location of the maximum is only 1.8 degrees to the right and 1.8 degrees to the left, which is approximately 3.6. We can locate it more precisely right in here. We gotta look for the minimum value. See here. Okay, that's the first minimum. Let's see here. 0. Oh, I should look at here. Okay, look at the minimum of the intensity. The minimum of intensity is around here, 1.7 degrees. So it's 1.7 degrees to the right, 1.7 degrees to the left, 3.4 degrees. And we can start to keep track, right? Let's do that. So we can, I'm gonna even do a plot here. Here we go. I'm going to undo. Let's see. No, I'm not gonna undo. I'm gonna keep track of the width of this right maximum and plot it accordingly. Okay. So here what we have is 20 microns. Let's start again at 1 micron. And then we can go even better. Let's start at 100 nanometers, okay? Which is comparable to the wavelength of light. And then we keep on going higher. Okay, here we go. And I'm gonna plot that all the way down to 90 degrees. So you can have an idea how this function behaves in terms of the size of the aperture of the slit, the size of the slit. Right now, I am at almost 45 degrees. Here I am at 63 degrees. Okay, now I'm exceeding 100 degrees. Let's go to 90. That's the maximum we should worry about, right? 90 degrees. And you go. Yeah, do you see how spread out it is? If you put the size, if the size of the slit is 100 nanometers, man, the diffraction effect goes spread all the way down. Oh, let's plot it. It's easier to plot from scratch. It's going only until 20 degrees, right? Let me plot it again. Yep, insert. Okay, now we're going all the way up down to 90 degrees. And even at 90 degrees, the intensity is 91% of the top intensity of the diffraction pattern. So the smaller the slit is, the more diffraction effects we get. Now let's keep on increasing, no? And let's see. I'm not even going to record that. What is the width of this guy, because the intensity is so high, right? Now, oops. And now what was 91%, right? Now is 68%. Okay. Now it's 68%. So this thing is starting to become sharper. 300 nanometers. Okay, now it's 40%. What was 91% became 60%, and now it's 40%, right? 400. Next. Okay, and now we are getting a value here of 20%, a little bit less than 20%. And then I can start keep track of the size of the peak with against the diameter of the slit. That's what I want to do. Okay, and I'm gonna pick up this 20% intense with respect to 20% intense. But before we do that, I want to change, maybe it's here. Yeah, I want to change the size again of my marker. So you have a sharper fill. marker options right in here. Built-in, we have a sharper line there. I cannot go smaller than that, so you're in good shape here. Okay, this at 20%, we have an angle of 74.3. Okay, so I'm going to copy this one here. A, this is A, and then tip width, right? Width of bright maximum of the maximum spot. Now one more student here, and what I'm getting here, 73.2. But just half, that's half width, it's not width, not full width, it's half width. 73.2 degrees, right? Half width. Next one is 500 nanometers. And what we get at 20%? At 20%, we get 50 degrees, 50.1. $500. Okay, and I'm going to make my life easier here. Uh-oh, didn't continue. Yeah, we didn't continue. 600. Ooh, this one that I want. Here you go. Yeah, it's not behaving the way I wanted. Okay, so 500 is again 50.1. Let's go 600. Right? 600, we are getting 40 degrees. And then I'm gonna go to the next one, 700. 700. We get what? At 20%. We are getting 30 whatever degrees. 33.5. Yeah, still not. Okay, next in line here is 800. Just enough for us to have an idea of the value. 800 is around. I gotta put 800 here. Half width at 20%, okay, of intensity. 20% intensity corresponds to an angle of I cannot take a read here. Looks like it's 28%, 29 degrees. Yeah, 29 degrees. And now I'm going to go a little bit faster. Instead of 800 nanometers, I'm going to make 1 micron, just like I had before. Okay, 1 micron. Okay, 20 degrees. Right here at this spot. 22.9. 2 microns. Remember, it went too fast. Yeah. Now the peak has a width, a half width at 20% intensity, equal to 11.3. Are you getting the idea here? And I gotta put here is gonna be 2 microns. Here's gonna be supposed to be 1 micron. Nah, not doing that. 3 microns. Okay, 20% correspond to a 20% intensity correspond to an angle of 7.5. That's very small already, right? 3, copy and paste here. Now let's go to 10 microns. 10 microns is what? It's 0.01 millimeters is the resolution of your micrometer, of your regular micrometer. And then what do I get here? 7.4. Didn't change much, right? Oh, wait a minute. 3. Yeah, okay. We gotta go 3 microns. Okay, now I have to go to 4 microns. Oh, not here, it's here. Oh, whoa, whoa, whoa. This one here. 3 microns, we have 7.5 degrees. Let's go to 4 microns now. 4 microns, we change to 5.6. And now I'm going to go to 10 microns. It's gonna be a big jump. Oh, nope. Right here, 10 microns here. And getting sharper and sharper. 20% correspond to 2.2 degrees. And so on. You're getting the idea, right? One more, 20 microns. 20 microns has a 20%, always a 20% intensity of 1.1 degrees. And that's what 20 microns is. Okay, 30 microns. Now let's go 40 microns. Let's go another step. Oh, now, you know, it's becoming so, the width is becoming so small that we are getting anywhere between 0.6 degrees and 0.5. Let's say it's 0.55. 0.55 degrees. That's 40 microns. Okay. And I'm going to do even better, something better than that. Here you go. Going back to our equation, notice that what really matters in our equation, what really matters is the ratio of A to lambda, okay? That's what really matters, the ratio between A and lambda. So when I change A, I am in reality changing the ratio A by lambda. As A becomes larger and larger, as this ratio becomes larger and larger, the peak becomes sharper and sharper. Okay? That's how you should look at it. We have alpha here and we have alpha here, right? That's what alpha is all about. Is and that's what the intensity is all about. Is a function of A by lambda. Okay? And now we can go back to our, I'm going to put A divided by lambda. That's what we call a canonical variable when we are analyzing complicated equations. We try to find those canonical variables to simplify our analysis. So A divided by lambda is this ratio here. Okay, I increase my ratio from 0.66 to 66. And now I'm going to plot the width, the half width at 20%. 20% half width. Okay, and look how it decreases. It kind of decreases exponentially, right? It's an exponential decrease. Let's see if I can fit an exponential curve to this guy. It's faster. Actually, it's faster than exponential. Wow, it's faster than exponential. Okay. I do not know this thing. What can be faster than exponential? It really, from the curve fit, you can see clearly it's faster than an exponential. Did you get the idea? Let's do something else about that. No? About this graph. Okay. Here's our graph. I'm going to get a larger A over lambda ratio. Let's see this one here. A smaller, not larger, it's smaller. A larger width. That's still too large of a width for me. Let's go to another one. Here, let's go to this one here. Yeah. So here we have a dark fringe. Here we have another dark fringe. Here we have another dark fringe, and so on, right? Bright spot, central maximum. Bright spot, that's not the central maximum, it's the wings. That's another wing here. Okay? Let's do a mathematical exercise. In this mathematical exercise, I want you to find out, find the position using the above equation, comma, find the positions, find the position in terms of theta, of the dark fringes. Okay? That's an example that I can come up with you, right? Example. Treat that as an example. Just and then just apply your mathematical skills to solve this problem. All you have to do is to get, sine of all alpha equal to 0, right? That's where the dark fringes are located. Even better, I'm going to be more specific. Sine of alpha over alpha must be equal to 0. Condition for dark fringes, That's the condition for dark fringes. Okay. Very important, right? I cannot state that position for the dark fringes is sine of alpha equal to 0. I cannot do that. Because if I do that, I'm going to say that at alpha equal to 0, you're going to have a dark fringe, when in reality you have a peak there, right? A bright spot. You have a bright spot because the sine of alpha is the actual formula is the sine of alpha divided by alpha, right? So when you have sine of alpha divided by alpha, we exclude alpha equal to 0 in this equation. And instead, the solution becomes what? The solution becomes alpha equal to pi, 2 pi, right? 3 pi, m pi, for m equal to 1, 2, 3, and it should be plus and minus as well, right? Because we have the left side. Ideally, we should put plus and minus pi here. Plus and minus pi, plus and minus 2 pi, which correspond to negative values of the angle. And when I do that, remember, I'm excluding the 0 here. I'm excluding the 0 because at 0 pi, 0 times pi, we have a bright spot. And pi. And now I can find out what would be the angle theta, right? In which we will find the dark spots, the dark fringes. That's the relation. Let's go one more step. Lambda over A and pi sine of theta. That the condition, this pi cancel out with this pi, right? Pi cancel out with this pi. I'm going to write down in terms of here, m. And by the way, there is a condition for that too, right? So the sine of theta cannot exceed a certain value. And consequently, the m cannot exceed a certain value either. Don't forget that the condition must be the following, right? Equal, yeah, minus 1. That's the condition for m lambda over A. And plus 1. Okay. So there is this limiting condition for m. This limiting condition for m is this one here. A over lambda on both sides. Okay. On both sides of the negative and positive values, right? Let's do an example of this limiting condition. So remember the angle theta, right? Should obey that. And let me finish this one. I didn't finish yet. Theta is supposed to be arcsine of that argument, like that. But let's not forget that m lambda over A must be bound by those values here, minus 1 plus 1, which comes from sine of theta. Okay. So, example. Find the maximum value of m for, I'm going to do an example that's already in our spreadsheet here. Maximum value of m for A over lambda should be this one here, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. A over lambda equal to 3.33. Or A over lambda equal to 3.33. Solution. So, according to found not the maximum value, find the bounds of m, right? For m equal to 3.33. So because m is here you go, a over lambda is 3.33, right? Plus 3.33, right? Because m must be an integer number, the values of m should be from -3 to 3. Okay, so you're going to have only 3 solutions. 1, 2, 3 darks, right? On the right side and 3 darks on the left side. Let's see if we have that. Indeed. 1, 2, yeah, 3. Okay. That's what it looks like, right? Okay. 1, 2, and 3. That's what we end up getting here. And 12:53, one more student coming in. Not 12:53, sorry, it's 8:53. Nine. That is 8 minus 8. Okay, Pacific, here you go. Adjust my clock here. 8:54. Let's finish that. That's the maximum value here, right? Find the bounds of m for a over lambda equal to 3.3. Let's do another one. Let's find the bounds. Find the angle theta. The angle theta. Continuation of the previous, right? Angle theta. For maximum m, for the maximum value of m. Okay, the maximum value of m. Find the position, right? So let's so m should be 3, right? Lambda over a is 3.33 as well. 3.333. Oops. 3.33. 2 divided by 6 is 1/3. That's why you are getting this value. It's 20, right? 20 divided by 6, because this guy is 10 to minus 6. This guy is 10 to minus 8, 10 to minus 7. And okay, so I got everything here, and all I have to do is to crank up the numbers with my arc sign. Let's not forget this arc sign. This one is going to be approximately arc sign of 10. Two-thirds. 26 times 3. Yeah, it's going to be arc sign of 10. Let's see, we cannot have that, right? Arc sign of 10. A over lambda. Let's see what's going on here. Right. Okay, so here you go. It's not a, just recap, right? Is m lambda over a, right? M lambda over a. So m lambda over a is, should be 3 times 1 divided by 333. Three. Even better, what we end up having here is 600 nanometers. Minus 9. And what we end up having here was what? Going back again. Is 2 times 10 to minus 6. 2 times 10 to minus 6, all in meters. And we end up having 300 here, right? And we end up having minus 3 here, right? Because it's minus 9 plus 6. So we end up having with minus 3 here. 1, 2, 3 is going to be 0.3. What we get here is 0.3. And the arc sign, again, arc sign here, yeah. Arc sign, right? What we finally get is 0.9. 0.9. Okay, so this number is possible to calculate, right? I remember that was getting like arc sign of 10. There's no such a thing arc sign of 10, right? This value here on inside the parentheses cannot exceed 1. So let's now calculate what arc sign of 0.9 is all about. A sine 0.9. Okay, that's in radians, right? And then I still have to find out how many degrees that is. I'm getting 64 degrees. 64 degrees, which is the last max, the last dark fringe, the last minimum, is around here, this region, which looks like is reasonable, right? If I zoom in, let's zoom in here. It's very difficult to see that, but if I zoom in, we can see that there is a flat spot here, but it's a flat spot at the low end, right? And then it starts increasing. So it's somewhere around here. The graph is, oh, even better. The more I zoom in, the better I see it. So let's go again. Let's see the 64. 64, right? Now let's look for 64 here in this column. 64. Lots of data, right? 64, 64, 64, around here. Let's see if we can find the place. Oh, wow. Yeah. 10 to minus 7. Right here. See that? Between 64.1 and 64.2. And what I'm getting there again? Yeah, between 64.1 and 64.2. 64.15. So that's where you locate the maximum, the point, the dark fringe that furthest from the central maximum. It would be very difficult to recognize that here with the naked eye, because the intensities that are that's nearby it is very small, right? Here is only what, like I told you before, right? Only 4.6% of the brighted spot. This one will be what? Even smaller. Wow, only 1.6%. So it would be very difficult to see this fringe here. And if it's difficult to see this fringe, it's going to be even more difficult to locate the dark fringe. Oh, 903 already. Let's go and get our. So practice a little bit with this function. Understand how it works because we're going to be using it. Let's see what's going on here. Can you hear me, by the way?
I can hear you.
Yeah, okay, good. So let's see. I cannot hear anything from the computer. Let's figure out what's going on here. Let me pause the. Okay, my earphone apparently went dead. So let me charge it back and we can go back to our class. Okay, so 64.15, right? Just to remind you, right? The exam 2, those are the sections for exam 2. And for exam 3, I'm thinking about including lab 1, maybe lab 2, okay? For the exam 3. But exam 2, yeah, you gotta concentrate on that. That's your priority for tomorrow. And let's do another interesting problem, right? Okay, example, find the angle theta. Let's see. Find the position of the dark spot if A equal to lambda. Okay. Find the angle theta, right? Angle theta of the dark spot if A equal to lambda. And go back here to my equation, right? We go if A equal to lambda, then this ratio here is supposed to be 1, right? If this ratio here is 1, the maximum value, the maximum and minimum values of M is going to be plus and minus 1. You're not going to have a second minimum. You're not going to have a second dark spot because sine of theta cannot go above 1, cannot be below minus 1, right? So the only possible values of M is going to be plus and minus 1. Okay, for sine equal to plus and minus 1. Sine equal to plus and minus 1 means what? Means that theta can be either at plus and minus 90 degrees. Does it really matches with our plot? Let's take a look at our plot. Here you go. I put the size of my slit is equal to 600 nanometers, which, by the way, is equal to the wavelengths of the lambda, and then plot the graph, right? And that's what we get. We have this broad diffraction pattern spreading out from 0 degrees until 90 degrees. And we do have a value. We don't have exactly a value of 0. Actually, the value is 1.52 times 10 to minus 33, which is enough, right? Which is close enough to 0. If we go all the way down here in this, see, that's the value that I'm getting here. If we exceed a little bit, what's going to happen? Yeah, if we exceed a little bit, then the intensity starts increasing, right? It goes from minus 33 to minus 12. right? So it's going to be, apparently it's going to be, yeah, exactly the same value. Yeah, it's symmetric with respect to 90 degrees. It's just gonna repeat all the way around. That's where you get the dark fringes for that specific value. And now we can start talking about other things. Now that we investigated this, how this function behaves, now that we know the behavior, more or less the behavior of this function, we can start talking about other things, right? Related to the other things related to that. We can start talking about the resolution of optical instruments. Okay, resolution of, even better, I'm going to put here, resolution of single slits and circular apertures. We have been talking about resolution in physics, right, in our lab. So I mentioned to you that what's the resolution of the ruler, right? What is the resolution of the ruler? That this resolution of the ruler is 1 millimeter. Anything less than 1 millimeter is very difficult for the rule to measure precisely the value, the length of the object. If you go to another device, hopefully you were exposed to this device I'm talking about, the resolution of the vernier caliper. Vernier caliper, right? What's the resolution of the vernier caliper? No, it varies, depends on the vernier caliper that you get. But in general, the simplest vernier caliper they're going to get out there has a resolution of 0.1 millimeters. Anything smaller than that is difficult for the vernier caliper to measure precisely. Then we have the resolution of the micrometer. The resolution of the micrometer is going to depend on the micrometer that you have, right, that you use. The micrometer that you saw yesterday has a resolution of 1 micrometers, right? But the more, the micrometer that we see more frequently has a resolution of 0.01 millimeters, which, by the way, is 10 microns. And then we also have the optical resolution of instruments, or optical instruments. Okay, for instance, the eye has an optical resolution. You can resolve, and what does it mean by optical resolution, right? Let's see. What is the optical resolution of an instrument, right? Or aperture, not just an instrument, but the aperture of a given instrument. Of the aperture, what's the resolution of the aperture of a given instrument? The optical resolution of an instrument will depend on its aperture. We can answer this question, okay? We can answer this question in terms of the diffraction theory that we have been discussing. And let me explain how do we do that. But even better, okay? The optical resolution of an instrument, and I'm going to define it. I want to be specific, and then I will be able to answer this question, okay? It's going to be, it is the smallest angle that you can resolve two different point sources. That different point sources. And this minimum angle, this smallest angle, we will be able to find out by referring to the diffraction theory that we discussed so far, okay? So let me illustrate what I mean. Okay, here you go. I have an illustration here. Maybe I have this other illustration. Let's see. I think I have it here. If I don't have it here, I'll have to show that other one. Yeah, I don't have it, unfortunately. Yeah, let me show you this one. Yeah. So suppose that we have two sources. Okay. Two stars close by each other, the headlights of a car, the two headlights of a car, right? And then you have this light going through an aperture, and those lights are going to be projected on behind this slit. The slit or aperture in general. The closer, the smaller the angle that you have here, the more difficult it would be for your aperture to resolve those two light sources, okay? And this aperture, by the way, I'm going to give you an example of this aperture. This aperture can be the aperture of the eye, the diaphragm of the eye, right? The iris, the pinhole of the eye that lets the light pass through, that little black P that's in the eye that opens and closes, depending on the illumination, right? And this screen that you see here can be, for instance, the retina of the eye. The retina is just like a screen that you project an image. And the brain picks up that information, that image, and translate that to you. Okay, translate that for you. Now, how do we define this angle? That's the critical question that we have to make, okay? But first, you have to understand what is optical resolution. Optical resolution is the ability of a given instrument to resolve two light sources that are very close apart. Okay, the closer those light sources are to each other, the more difficult it is to resolve those two sources. The closer those two light sources are to each other, they're going to, the more they're going to appear to be a single light source. And there must be a criterion to determine this angle theta. And how do we determine this angle theta, right? There is a criterion that I'm going to present that to you. So here you go. We have two light sources, okay? Light source 1 that's going through the aperture, and light source 2 that also goes through the same aperture. And they leave behind this diffraction pattern in the screen, okay? So now you can start having an idea how you can resolve those two light sources, right? If the angular separation of those two light sources is in this case less than 1 degree, less than 0.01 degrees, okay? You have a peak here, you have another peak here. This peak is a 0 degree angle, and this other peak is, let's say, 0.08 degrees. Okay? At this point, you will be able to resolve those two light sources. You'll be able to tell, okay, we have two light sources here. They're very close to each other, okay? But note, see here what the first minimum is occurring for the light source 1, right? The first minimum of the light source is almost overlapping the first minimum of light source number 2. Minimum of source 1, minimum of source 2 as well. Okay, how close they have to be so we can, resolve them. Now, what about now? Suppose that those light sources are so close to each other that their peaks are almost overlapping each other, right? In this case, the diffraction that's going to be projected in the screen is going to be the diffraction of a single light source. You won't be able to resolve. You're not going to be able to say, look, this is two light sources. No, you won't be able. Because this intensity here is summing up with this other intensity. And the peak is going to look like the peak of a single light source, okay? So in this case, they cannot be resolved. Okay, so to find out the resolution of any aperture, we use what we call the Rayleigh criterion. Did you get the idea? And let's see what's the Rayleigh criterion. Remember the criterion that I mentioned to you. I just didn't tell you what the name of the criterion. Let's write it down, okay? Move this one. Notes right here. What's the optical resolution, okay? We can answer this question in terms of diffraction theory you have been discussing. Okay, so here you go. Let us cover in a qualitative fashion, right? If the angular distance, right? If the angular distance of the two light sources are far, is large enough, then it will be possible to distinguish two different diffraction peaks at the screen behind at a screen, right? A screen behind a slit or aperture. Okay. So we have this example that I mentioned to you. The angular distance of the two light sources is large enough, then it will be possible to distinguish the two different diffraction peaks at the screen behind a slit or aperture. And then I'm going to, that's the case in which it's possible to distinguish the two peaks. Okay. The two diffraction peaks are far enough to be distinguished from each other. Okay. However, so the resolution is just a matter, it's just the resolution of a given eye, is going a given instrument. This thing exists just because the diffraction characteristic of sources, okay? If diffraction didn't exist, if light would behave just like particles, you wouldn't have that light spreading out over a given angular distance, right? And everybody would have a very high resolution, optical resolution. However, if the two light sources, if the angular distance, right? If the angular distance of the two light sources is not large enough, if the two light sources is too close, right? Let's put it this way, it's too close, then it will be difficult to distinguish the two different diffraction peaks at the screen behind this little aperture. And you will think that the resulting diffraction peak is due to a single source, okay? And that's the other drawing that you want to have in mind. And by the way, I plot that in Excel, okay? That's something that you can do in Excel. Now we have a peak here and another peak here that's very close to the other one. When you sum the two peaks, the two intensity peaks, you're going to think that you have just one light source. So now how do you quantify the resolution, right? To quantify this resolution, we use what we call the Rayleigh criterion. What does it state? Which states the following. One, here you go. If the central peak, central maximum, right, or central peak of one of the images coincides with the first minimum of the other image, then it will be possible to resolve the two sources. That's the Rayleigh criterion. I'm going to illustrate that too. Okay. So if you have a situation like that, Rayleigh criterion. So here you go. We have one peak that's located, at the position of the first dark fringe of the other image, and the location of the second peak that also coincides with the first minimum of the other source. If you have a situation like that, your image is going to be a little bit blurry, but you will be able to recognize that you have in reality two light sources, because you're going to see two different peaks in this diffraction image. Okay, that's what we have. That's the criterion that we have to use. Okay, and let's see some images. Here's your book. Okay, your book has a nice. Okay, here you go. See, here's the case in which the two light sources, the angular, right, separation of the two light sources is too close, and the two peaks are almost. You cannot. It's so close to each other that we see just a single peak. Okay. As two images of 2-point source formed by a converging lens. Converging lens has a given diameter, right? And can be sought to, the diameter of the lens can be sought to be the aperture. In A, the angular separation of the source is too small for the source to be distinguished. B, they can be marginally distinguished. In this case here, they're almost fused, right? But you still can make up a little bit of a difference here. And then we have this other situation in which the diffraction diffraction image of the two sources are far apart enough for you to clearly distinguish two peaks. Okay? And that's what the, okay, and then we're going to come up with this angle of separation. And how do we do that? Right? Relate this. We have to find, we have to find what's going to be the position of the first minimum of the source. Going back to our right here. This equation, right? This equation, right? The first minimum occurs at m, first minimum occurs at m equal to 1, or so that's what we have. I'm gonna put it here. Minimum. Oh, it doesn't like that. Amanda. Okay, we can come up with our approximation for sines, right? So we can state that for the small angle application, right? That the minimum is approximately equal to that. But by the way, and that should be an approximation as well. But by the way, what you see here is an equation that applies only to a slit or a rectangular aperture. Okay? That's what the above equation is all about. We did that derivation for a rectangular aperture, to a slit. For a circular aperture, like the pupil of the eyes, right? Pupil of the eyes, for a circular aperture, this formula is slightly different. It's slightly different. I'm not going to derive it here. Different, but it's easy to remember. Instead of 1 times lambda over A, that's going to be 1.22 lambda over A. That's what the Rayleigh criterion is for a circular aperture, only 22% more. Shouldn't be difficult to memorize that, right? And that's what we have here as well. Right? Rayleigh criterion. So now we can start figuring out what's the resolution of the human eye. Resolution of the human eye. Remember, the resolution will increase as the aperture decreases. The size of the aperture decreases, right? Also, the longer the wavelengths, the larger the minimum. The diameter of the pupil of the eye, of the human eye, the diameter of the pupil of the human eye varies from 2 millimeters to 9 millimeters. In the dark, In a very dark environment, it's going to be very dilated, right? In a very bright environment, it's going to shrink to 2 millimeters. That's what happens to the pupil of the eye as it controls the amount of light that passes through, that goes towards the retina. And the human eye, is sensitive only to visible light, right? Visible light. And visible light should be in the range of 400 to 700 nanometers. Let us find out, what's the range of resolutions. It's not just a single number. It's actually a range of value, which depends on the size of the pupil, depends on the wavelengths of the light as well, okay? So the situation is like that. An equation, here we go. Lambda is somewhere between 700 nanometers and 400 nanometers. And we also have A. A is anywhere between 2 millimeters and 9 millimeters. Okay. And now let's apply those values. And by the way, lambda over A, right? We can even go ahead and find out what would be the range of lambda over A. What's going to be the range of lambda over A, right? The smallest lambda over A is going to be 400 divided by 9, 400 nanometers divided by 9 millimeters. That's going to be the smallest ratio. The largest ratio is going to be 700 nanometers divided by 2 millimeters, right? And then we have to multiply that by 1.22 to have the limiting resolution of the human eye. If we do that, limiting resolutions of the human eye. But don't forget, this is an angle in radians, okay? Here is going to be 10 to minus 9 meters. Here is going to be 10 to minus 3 meters. Here is going to be 10 to minus 9 meters. Again, here's going to be 10 to minus 3 meters. Let's look at the left side of the equation first, right? The smallest is going to be this one, right? That's going to be the smallest. That's the limiting, the very limiting. But again, it's going to depend on the wavelengths. If you have blue light at 400 nanometers and your eye is fully dilated, you're completely in the dark, you're going to have the best possible resolution. The best possible resolution. Now, in a bright environment, at a wavelength that's close to the red, almost in the infrared, you're going to have the other limit of your resolution, of the human resolution. Let's get these numbers here. What's that? I'll get this. I'm going to copy and paste in my spreadsheet so we can calculate that. 1.22 400 divided by 9, that's going to be e to minus 6, right? Nope, didn't like it. 10 to minus 6. That's what I'm getting. 1.22 400 divide, I put divide by 2, huh? Supposed to be divided by 9, right? Divided by 9, 10 to minus 9 plus times 10 to minus 2 plus 3. That's why I'm getting 10 to minus 6 here, right? So I can put a minus 9 divided by 10 to minus 3. And that's what I'm getting. 10 to minus 3. Let me put here this. Right, and I'm going to make sure that I put my parentheses here. What about now? I'm getting 5.42 times 10 to minus 5 radians. Let's see in degrees how much that is. Hopefully this number is correct. Okay, let's see, that's degrees. That's a second of minutes of arc. 0.186 minutes arc minutes. Okay, that's one limit. The other limit is going to be 1.22 times 700 times 10 to minus 9 divided by 2 times 10 to minus 3. And that's what I get. Okay. So it's anywhere between 0.18, 0.19 to 1.46 arc minute. Ideally, the ideal would be this one here, right? If you are in a very dark environment and you're looking at light, 2-point lights that are blue, the blue end of the spectrum. The longer the wavelengths, the more it's spread out in the screen. Okay, the lowest, okay, the lowest possible resolution, right? It should be 0.18 or 0.2. Let's approximate that to 0.2. 0.19 arc minute. I'm gonna put arc minute is like that. We represent by that. And the other one was what? 1.46, 1.5. Let's put 1.5 arc minutes. Arc minute, not arc second. Arc second is even smaller. If you want to remember, you know, if you want to average this value and remember an easy number, we can state based on the above results, we can say that the average resolution of the human eye is 1 arc minute, which is a number easy to remember, right? 1/60th of a degree. That's what 1 arc minute is, which is 1 divided by 60 degrees. And then you have these telescopes. We can also calculate the resolution of a telescope mirror. Limited by diffraction, right? Limited by diffraction. So let's see, what's the largest telescope out there? During my time, when I was growing up, the largest telescope that we had at the time was the Mount Palomar, the telescope at Mount Palomar, nearby San Diego. I was there several times. 5-meter diameter. And then the Russians built a bigger telescope, a 6-meter diameter telescope in the Caucasus Mountain, the Soviets, right? But now, those numbers have been surpassed, by a large margin. Largest telescope mirrors, telescopes, largest telescope in the world, here. Gran Telescopio de Canarias. Canarias is there in the Atlantic Ocean. Canary Island belongs to Spain, right? The largest optical telescope in the world with a mirror that has a diameter of 10 meters. It's located at the Roque de los Muchachos Observatory on La Palma, the Canary Island of Spain. 10 meters. Let's calculate what would be the resolution of this telescope compared to the human eye. 10 biggest telescopes on Earth, huh? Space.com, let's see, 10 biggest telescopes. These giant terrestrials have our planet eyes. Let's see, biggest telescope on the Earth and the most successful at making new space discoveries. Hubble Space Telescope was what? 2 meters diameter, right? What about the James Webb? That's orbiting Earth right now. Let's see, diameter. What's the diameter of this mirror? Anybody know the diameter of this mirror? L2 orbit, primary size mirror. Okay, 6 meters and a half. Okay, 6 meters and a half. So a little bit larger than that telescope that the Russians built several years ago. Okay, so let's stick to the 10 meters, right? We have more. Let's see, 10. Hobby Eberly. Okay, 10 meters. See, 10 meters. It must be the Mauna Kea. See that? That's the Mauna Kea, like there in Hawaii. Keck telescope in Mauna Kea. Optical and infrared. Close that. Next, Gran Telescope in Canarias, 10.4. It looks like it just surpassed South African Large Telescope. 11. Oh yeah, the telescope of Canary Canary Island was surpassed. Now this in South Africa is 11 meters. Let's see, Atacama, 12 meters. Hey, that information was not updated, right? And then we have this one in Chile. Are they building or is already? Let's see, the GMT set. See, it's just not complete yet. Yeah, it's almost 30 meters. What about the other ones? Let's see, 12 meters, 60, but it's a radio telescope. Oh man, he's talking about radio telescope. I don't want a radio telescope. I want an optical telescope. That's optical, okay? This is the radio telescope. Radio, see that? I don't want an optical. This still has to be completed. Optical, Atacama Desert in Chile. This one, 30-meter telescope, TMT, Hawaii, 30 meter is an optical infrared. Good. 30 meters. Is it completed already? This project is currently in progress. Okay. So it's not complete yet. Square meter array must be a radio telescope. Yeah, it's a radio telescope. It's easier to make a large radio telescope than to make large optical telescopes. The name, let's see, extreme large telescope, extremely large telescope. Let's see, 139 meters, designed, optical infrared, due to completion 2027. And then we have the spherical telescope, 500-meter aperture spherical telescope. Radio is a radio telescope. Okay, so let's get. We're going to calculate the resolution of the telescope of an optical telescope that is already in operation. Okay, this one is already in operation. No, that's radio telescope. You don't want that. Optical. almost identical to Hobby Eberly because it was inspired as the South has the number of hexagonal panels. Let's see. Yeah, this looks like this guy is already completed, right? In Karoo, South Africa, large telescope. 11 meters. Yeah, so let's use 11 meters. And let's calculate that. The aperture. See, the larger the aperture, the smallest the resolution, right? And the smallest resolution means what? The smaller resolution means the more powerful the resolution is. The smaller that number is, the more powerful the resolution is, okay? And that's gonna be 11 meters. Okay, I'm going to put a wavelength that's the shortest possible, times 10 to minus 9, which is in meters as well. And we're gonna crank up this number and figure out what would be the resolution of this guy here. Okay, the human eye is 9 millimeters, right? 9 millimeters is 10 millimeters. 10 millimeters, so 11 meters should be 1,000 times more. Okay, 11 meters should be 1,000 times more than the human eye. A little bit more than 1,000 times. Here's 1,100 more, 1,100,000 more, 1,100 times more. 1,100 times more would be, you know, man, in the millimeter resolution, right? Which is this number is 1,100 times more than the more powerful. Let's put it this way: more powerful. 1,100 better, right? 1,100 times better than the human eye. Human eye. And where did I get that again? I divided 11 meters by approximately 10 millimeters. 10 millimeters, right? Approximately. It's a little bit more because it's not 10 millimeters. The human eye is 9 millimeters. I'm just rounding that up. If I want to know the exact value, right? Let's 11 meters divided by 9 times 10 to minus 3. 1,200 times more. 1,200 times more. Okay, 1,200 times more should be, let's say, 0.2 arc minute divided by 1,200. Right? That's arc minute. We can multiply that by 60 to determine in arc seconds. Well, it's sub-arc seconds. So that's the resolution of this telescope, okay? 0.009 arc seconds. Okay. 0.009. 0.098. 0.098 arc seconds. We abbreviate by this symbol here. Okay, so that's the resolution. Okay, that's what we want to do, and that was done also in this book. Rayleigh criterion for resolving two distant objects. He's applying the Rayleigh criterion to this length. Okay, this length has a diameter of 32 millimeters. We just did for 11-meter diameter telescope. He's doing for this specific wavelength 550. Again, remember the resolution is going to depend on the of the wavelengths and the diameter of the telescope. Diffraction by a double slit. You go. We did that, right? Yeah. Yeah, we did this one here. All you have to do is to, yeah, I did that last time, remember? You have to put this term here to modulate the resolution of the intensity of a double slit. Okay, here's what we got without accounting for diffraction. In order to account for diffraction, we have to multiply this term by this other term here. That's all you have to do. And when you do that, that's what you end up getting. Oh, here you go. That's what you end up getting, right? Here's the intensity that if you don't account for diffraction, here's the intensity variation for a single slit. The diffraction pattern of a single slit. When you combine those two, you get something like that. Okay, you have this modulation in what here you go. This modulation inside this diffraction peak, right? So this modulation that you see here is ends up being here. Notice that the degrees here is the same, right? It's minus 20 degrees to 20 degrees. So when you multiply this by this one, you get all those peaks here inside that are modulated in amplitude. Here's the minimum of the diffraction. And then you have the other little peaks that are also modulated due to the double slit. Here you go. That's how it looks like in real life. That's how the double slit looks like in real life. Interference fringes for an actual double slit system. Diffraction pattern of a single slit, right? That's the single slit, that's the double slit. There is, in the single slit, there is no modulation here inside this bright spot, right? But with the two slits, you get that modulation in every spot that you see. Central diffraction and then the side diffraction spots. Okay, those. What time is that? 10:15 right now. Let's take a look at our break. Any questions about that? Ideally, we should be doing those experiments for you to see, okay? That's the ideal case. But at least we have pictures here. And those things exist, you know, that we can buy those slits rather easily. That last break started at 9:23. So we're almost 1 hour there. And let's see how is attendance here. 14. My roster, and yeah, it looks like one of the students left. Okay, I'll let him get away with that for now. Break. Any questions before we go to the break? Let's do 10:20 a.m. to 10:35 a.m. And don't forget 12 noon, we have another lab. And so far what we have covered, we have 1 more minute to do that, right? Let me just that's chapter 36. Single slit diffraction, 36.1, 36.2, 36.3. We did that. There is this one has an approximation there. We didn't prove that value, but there is this approximation 1.22, and then we elaborated on those values, right? And diffraction grating that we're going to do. Oh, diffraction by a double slit. It's kind of straightforward. It's just a matter of multiplying one by the other. And that's what we did so far. And what about interference? Let's 31, 36, 1, 2, 3, and 4. Yeah, 36.1 through 36.4. And then I'll give you the sections that we did for the other chapters, okay? Covered. So I see you in 15 minutes. Okay. Okay, so here you go. What's important to have in mind? Okay, the smaller the angle of resolution, the better the resolution of the instrument, right? Is that how we say? And that's why I'm not using 1100 times more than the human eye. No, there's not. What I mean is that 1100 times better than the human eye, right? The telescope of 11 meters has a resolution that 1100 times better than the human eye. We don't say more or less, right? Because you can get confused. The smaller the number, the better the resolution is. This resolution here is better than a resolution of 0.1 second arc. So the smaller the resolution here that we have, the better the resolution is. Okay, that's the important thing that you gotta have in mind when we are talking about resolution. And we're going to look at diffraction grating now. It's an important type of grating that we use out there. We use for spectroscopy. And it has a rather simple theory as well. And how does it work? Okay, so diffraction grating now. That's something that can also be bought easily out there. Let's take a look at diffraction gratings out there in the market. Diffraction gratings. Okay, here you go. This is one of them. Professional diffraction grating. Do you see the rainbow color here? That's exactly how it looks like. There's a grating transmission. That's a transmission, okay? That's in Portuguese here. And Tor Labs, for instance, sell those diffraction gratings. There are diffraction grating transmission and reflection. CDs, you know, those CDs discs, right? They act just like a diffraction grating. They behave just like a diffraction grating. Let's take a look at Tor Labs catalog here. There are other places that sell those too. This is a transmission. Great, oh, they have Portuguese here. Let me, and those are in reflection. Let me explain to you exactly how those things are built, okay? The grating. I need to get a good illustration here so you can understand. You already know how a double slit film works. I cannot find here. I have to draw it from scratch for you. Oh, okay, now let's yeah, I'll have to draw it from scratch. I'm supposed to have that here. Let's see if I have somewhere else. Yeah, okay. Here is a grating with a single aperture, right? Also a diffraction grating with a single aperture. And then the double slit experiment is a grating with two apertures. Here you go. And then, oh, I found it, right? Here you go. I found it right in here. And here we have a grating with 1, 2, 3, 4 apertures, right? And then you can have gratings with 10, 20, hundreds of apertures out there. That's the type of grating that we are talking about. That's the diffraction grating that we are talking about. It's just like a little slide that you saw there, okay, with a bunch of lines, black lines. It's a transparent film with a bunch of black lines in a single direction. That's how they look like. That's how those diffraction gratings look like. Diffraction grating under transmission, right? And then you have the diffraction grating under reflection, which is just a bunch of surfaces that reflect light, but so you have lines, reflective lines that are very close to each other and separated in the reflection grating, right? Lines that reflective lines separated by lines that do not reflect. And CDs are just like that. And they have some very neat interference properties. Okay, here is a diffraction grating, an illustrated diffraction grating under transmission. A lot, you know, a light wave comes and passes through each of those holes. And the idea is exactly the same. You have this light ray that goes from this point to this point. This other light ray that goes from this point to this point and interferes the first light ray, and so on. Okay, that's an idealized diffraction grating, but just 5 rulings. The distance here to the screen is much larger than the separation of the gratings, and there is a very nice interference pattern that formed. As before, we have this maximum, the central maximum, but then you have a bunch of others adjacent maxima to the left and to the right. If you're using a monochromatic light source, that's the type of pattern that you get in a screen. M equal to 0, 1, 2, 3. Here should be -1, -2, -3, okay? And that's how the intensity looks like. The intensity is like a very sharp curve. Bright fringes seen on the screen are called lines, and are also labeled with order numbers M. Okay. And how do we model this type of situation? Okay. So note that we have a separation between each of those lines, right? And the path length difference between each of those lines is going to be d sine of theta, just like we had before. And if you want to have a bright spot, this sine of theta must be equal to m lambda, right? Diffraction gratings. Let's write that down here. P39 notes. A diffraction grating under transmission is a device, is a transparent piece of plastic that has several black lines written parallel to each other. Okay. In between these lines, we have the transparent aperture, right? It's not exactly an aperture because it's a solid surface through which the light can pass through and interfere with the other light, with the light rays that pass the other apertures. Okay, like that. This type of grating produce an interference pattern onto a screen. The path length difference can be written as d sine of theta, d sine of theta in order to get the constructive interference. And by the way, where d is the separation between lines in order to get constructive interference, comma, equation must be equal to m lambda. Like that, or equal to m lambda m, where m is equal to 0, comma, plus and minus 1, plus and minus 2, etc. And I'm going to put a bright spot. So what are the applications of diffraction gratings? Applications of diffraction gratings. One of the application, an application of diffraction grating. In spectroscopy is in spectroscopy. Not applications, application. I'm gonna mention just one application, but that application is broad enough, okay? It's spectroscopy. By the same token that you can break down white light into multiple colors using a prism, comma, you can do the same with the diffraction grating. Okay. Let's take a look at how many those diffraction grates that are usually sold with the number of lines. Okay, let's see. Characteristics. Let's take a look at this diffraction grating here. There at the Lake Harbor, we have a bunch of those things. Those things are made in mass and groove density available. Okay, here you go. So here you go. We have 300 grooves, let's say 300 lines per millimeter, anywhere between 300 and 1200 lines or grooves per millimeter. That's how advanced the technology has become. We can make grooves that are very close to each other. Okay. Graphs. Let's take a look at the graphs. This is efficiency. We don't want that. Okay, overview. Let's take a look at grating tutorial, what they have here. Okay. All in English now, right? Transmission grating. See the little groove here? It's like the line that's diffracting the light. And here is the A is the separation between the lines or the groove. Same equation that we are using. Okay. And then we have the reflective gratings as well, which, by the way, works almost the same way as the other one. Blazed gratings, that's another way of making a grating, a diffraction grating. Here's the separation. And then so on. There are little configuration for reflective gratings and so on, right? Let's see if we can see I want to show you how those gratings generate gratings guide. No, not what we want. Let's say image formed by a grating. Diffraction rate. Let's take a look at Wikipedia. Wikipedia usually has some good articles. Oh, it's taking a long time. Okay, so yeah, okay, so yeah, it's taking too much time. Let me show you those pictures here that we have. Here's how a prism works, right? Need a better image here. Okay, white light goes through a prism, and due to the different speeds of different colors in the glass is capable of breaking down the white light into multiple colors, right? But the grating can do the same. If you have white light incident on those gratings, the grating is going to produce constructive and destructive interference at different spots. And because of that, it can break down the light in different colors as well, from the red to the blue. So whatever we can do is a prism, we can also do is a diffraction grating. It happens that diffraction grating, we can control better the how we separate the colors, the different wavelengths in the white light. Okay, so here you go. Incident white light. We have the zero order, the bright spot that we see all the time. The bright spot is going to be white light as well, but at the other angles, they're going to be able to break down the colors at different angle. And you are going to have first the first order, and then you're going to have the second order, and so on. Okay. Types of gratings and there are many spectrometers out there that use gratings, either the reflection or the transmission. So let's come up with an example. Okay, the first thing that you wanna, okay, example 1, right? A very simple example. Let's take a look here. Laptop is good. Okay. So the first example here. What is, theta bright, huh? Theta underscore bright, theta bright for a given wavelength if m equal to, I'm going to say for not a given wavelength, for any wavelength if m equal to 0. Think a little bit about that. Solution. We gotta use this equation here. I didn't give you the separation between the lines of the grating. All I want is for you to tell me what is going to be the theta bright if m is equal to 0, right? If m is equal to 0, it doesn't mind what the wavelength is, because the solution is going to be the same. You go theta bright, sine of theta bright equal to 0. D is different of 0. Consequently, at m equal to 0, the theta angle is going to be 0 as well. Okay, and then you can come up with another example. What is theta bright for wavelengths lambda 2, right? If for wavelengths of lambda 2, if m is equal to 1, okay. Now m is equal to 1. Consequently, we are going to have the right side is going to become lambda 2 only, right? And your theta bright is going to be lambda 2 divided by d. You have to know the value of d. Okay, and the theta bright at that specific wavelengths, for that specific wavelengths, is going to be the arc sine of lambda 2 over d. Let's be more specific, right? Let's get some numeric examples. Getting from a product that we have here. One of those products that we saw. That's Edmund Optics. Not this one. Let's see. I gotta do another search here because I'm in the wrong spot, I guess. Let's see. Diffraction grating. Okay, yeah. Here you go. Here's one of the pictures of a diffraction grating. See. Okay, here you go. Yeah, diffraction grating. We are passing white lights to the diffraction grating, and the grating is breaking down the white light in several of its colors. Blue through red, right? Red through blue, and here we have the maximum. That's exactly how it looks like, the central maximum. This is a diffraction grating under reflection. Under reflection, light comes here, is broken, reflects from the grating. It's broken down in different orders. Unlike the prism that have just a single variation in the wavelength, the grating you can have different orders. Central maximum here is white. The first M equal to 1 breaks down the wavelengths from red to blue. M equal to 2, you have a gap here. Red to blue, M equal to -1, and so on. That's how it looks like. That's exactly how it looks like. And happens under transmission and happens under reflection as well. So let's take a look at one possible grating here. Let's go Horiba website. Gratings, industrial applications. Let's see, read more. Place holograph. Let's take a look at this one. Specifications. Take a look at these specifications here. Okay. See group frequency ranging from 150 to 5,760 gratings per millimeter. Okay. Let's get 150. 150 per millimeter. Don't forget you have 150 gratings in a single millimeter. If you have 150 gratings in a single millimeter, we can find out what's the separation between two adjacent gratings, right? 150 gratings in a single millimeter correspond to a single separation in a given distance, okay? And then we solve this equation for D. D goes here, 150 goes downstairs. And now we're going to get this thing is a tenth, less than a tenth of a millimeter. 1 divided by 15. That's 150, right? Yeah, I got from the catalog, okay? Let me show you the catalog here. Here you go. We have this catalog here. See, they have gratings with a group frequency ranging from 150 to 5,760. Okay? That's what I got from one of those products of theirs. I believe they have downloads here, holographic grating. Yeah. Catalog, see? The catalog. But you have to request. So they don't let you keep a catalog right away. What did I do here? Okay, so should be here. Yeah. Okay, makes sense? So those things are manufactured. They have a bunch of those. They look just like little slides. And we have a bunch of those there at LA Harbor. Think about making 150 gratings, right? 150 lines in a single millimeter. It's possible to do that. We have technology to do that. And 1 millimeter divided by 150. Let's do the calculations here. 1 divided 150 is 0.0067. 0.0067 millimeters, by the way. 0.0067. Oh. 0.0067 millimeters. These correspond to what? 6.7 microns. Micrometers. 1, 2, 3. That's the separation. It's amazing that they can produce something like that. That's the distance between the lines, right? And now let's do that for 670 nanometers, okay? I'm gonna do like that. Apply the above, right? Apply the above, find the, let's see. Find the position of a 600, I'm doing here, my nanometer wavelength. Find theta, here you go, find theta. Of 670 nanometers for a grating with 150 grooves or lines per millimeter. That would be so the equation is this one here, solution, right? Solution. The equation is this one here, and then you can go ahead and plug in 670 nanometers here. D we have to find from this relation that you see right in here, which ends up being 6.7 microns. I did put 670. I did 670 on purpose, okay? So it's easier for us to do the math here. Microns. You gotta take the arcsine of that. If we do the math, we're gonna have 100 upstairs, but we still have the 10 to minus 9 here to worry about, right? And then the 6.7 is gonna cancel out the 670, but we still have to worry about the 10 to minus 6. 10 to minus 9 is nanometer, 10 to minus 6 is micrometer. And the angle, let's see, we're doing m equal to 1, right? Yeah, we're doing m equal to 1. So then you can do for m equal to 2 as well. When you do this math, you are going to get 10 to minus 3. Multiply by 100, you get 0.1. Arcsine of 0.1. And take the arcsine of 0.1, a sine 0.1. That's what we get for in radians, and then convert that to degrees. .7 degrees. 5.7 degrees, right? That's the position at m equal to 1. For m equal to 1, right? But we can also have the same wavelength at a different angular position if m, find theta for m equal to 2. Okay? You can repeat that for m equal to 2. For m equal to 2, just like that, the m is going to go inside the argument here, right? The angle is going to be larger, right? 2 times, let's see, 2 times, oh, it's going to be 0.2 now. I don't even have to do the math, right? Most likely it's going to be around 11.4 degrees. What you see here is lambda over d, right? What you see here is lambda over d. And all I have to do is to multiply by 2. Multiply this value by 2, and you get 0.2. And most likely it's going to be around 11.4 because it's small angle approximation, right? So let's get this one here. No, not this one I want. I want the other one. Okay, so let's compare. Now I'm gonna put 0.2 here. And what do we get? Yeah, 11.5. Almost twice as much. That's the small angle approximation. Okay, 11.53, 54. Four, like that. And then you can have theta for m equal to 3, m equal to 4, okay? That's the advantage of the gratis. You can have several spots where to look for the different wavelengths. Yeah, 5,607. Yeah, I don't have a clue how they make that. Okay, I really don't have a clue how they make it that. I can just, imagine how they do it. One way that I can think that you folks might visualize, right, is to go ahead, make several lines very close to each other in the paper. Okay, black lines very close to each other and also evenly spaced, right? And then you go to your photocopy machine and photocopy that grating into a transparency. There are some transparencies that can take the photocopy, right? Oh, and then they just keep on shrinking that transparency paper with the gratings more and more. But they must have other better techniques. Okay, how many orders are there for M? Infinite numbers of M, okay? It all depends on the light intensity that you have. The more intense the light, the more the greater the order of M you can have. And also the more grooves you have, right? Take a look here at the equation. The more grooves you have, the smaller the D becomes, right? The more grooves you have, the smaller the D becomes. Right, let's take a look here. Yeah. The smaller the D becomes, the larger the angle is, right? The larger the angle is. So up to which M can we do it? It's going to depend on the intensity of the light. Because as you go further in the order, the intensity of each of the orders decreases as well. In principle, it can be infinite numbers of M. But also don't forget, right? The smaller the separation between the gratings, the more separated the orders become as well, the angles. So we can do that, right? Let's consider, let's do an example. What is the angular separation, right? between m equal to 1 and m equal to 2 for wavelengths, for a 607 nanometer wavelength and 6.7 microns, and d equal to 6.7 microns, like that. Okay? So what you have to do, no solution, right? Let's see what's angular separation. First, we do that for m equal to 1. And then we do that for m equal to 2, right? Oh, we already did, right? Here you go, we already did. We did for m equal to 2 here and m equal to 1. So you don't have to redo the calculation, right? For m equal to 2, for m equal to 2, what's the angular separation of the bright spots of a 670 nanometer wavelengths between m equal to 1 and m equal to 2, right? And d equals 6.7. So we already did, right? For m equal to 2, we found that the bright spot at that specific wavelength is 11.54. That's bright. I'm going to abbreviate here my notation. Bright spot. And then we also found that the bright spot for m equal to 1 is 5.7 degrees. Right? So now you subtract those two. They're sort of close to each other. It's a small angle. It's going to be around 5.75 degrees. No, that minus that is going to be minus that. And then you do the math. It's going to be around, what's that going to be? 5.8. Looks like 5.8 to me. Yeah, 5.8. 5.84, right? 5.84. And then you can do for m equal to 3, 4, 5, and so on. Let's take a look what we did here so far. So that's what this section is all about, right? The more important is for you to visualize how this thing is done. And you go, the intensity is a very sharp line. Okay. And that the data theta between them. Okay, grating spectroscope. That's one possible application of the grating. Light source goes through a lens and it is focused. Okay, it's focused into the grating. S1 is the grating, right? Simple type of grating spectroscope used to analyze the wavelengths of light emitted by source S. Yeah, that's the grating here. And then this light is collimated by this. Oh, no, the grating is this one here, sorry. Here's just a pinhole, Okay, so this light is collimated by another lens. And that's the grating, okay? As the collimated light passes through the grating, this is a transmission grating, is going to separate different wavelengths from the source here, coming from the source. It can be, the source can be a star, okay? A faraway star, can be the flame of a candle. And when you separate each wavelength, you can have an idea of what are the atoms that the source is made of. Here you go. What about the hydrogen lamp, right? There are lamps out there that uses gases. And if you have a gas, hydrogen gas along inside contained in a bulb, not a bubble, but a bulb. Okay. And you pass some electricity to it, it's going to start to emit, it's going to start to glow. That's one of the first types of light sources, electrical light source that we invented. And that's what we call the arc lamp. Arc lamp is made of different gases, hydrogen, helium, neon, okay? So if you go ahead and get the light produced by this arc lamp with hydrogen atoms inside, you're going to get a spectrum that's going to look just like that. At 0 degrees, it's going to be the bright spot, right? And then you're going to see all sorts of different lines, right? In the violet, blue, green, and red. Hydrogen atoms, they emit light at a specific wavelengths, at those specific wavelengths. At m equal to 1, it's going to look just like that. You can project that onto a screen. As you increase the angle, right, that will be between 10 and 20 degrees. Then you're going to have the same lines, same colors, but they're going to be of a different order. Okay, they look that they're more separate, but it's just an optical illusion because you are using a strip, a flat strip. Okay, do you see? It looks like that this line is the angle is greater than this angle here. Well, it's not greater because it's just an optical illusion, because what you see here is a flat surface and not a curved surface. If it were a curved surface, you'd be seeing that this angular separation would be exactly the same as this angular separation. So it's a distortion of the screen, right? This screen causes distortion. M equal to 1, M equal to 2, and then M equal to 4. For some reason, it didn't show the M equal to 3. The zero order, first, second, and fourth orders of the visible emission lines from hydrogen. Note that the lines are farther apart at greater angles. They're also dimmer and wider, although that's not shown here. Here we go. That's how it looks like, those lines. Cadmium. This one is for atom of cadmium. Violet, blue, blue, green. I think that they omitted by mistake, because if you see M equal to 4, we're supposed to see M equal to 3. It's difficult to know why they omitted that. It's difficult to know. I wouldn't have omitted, if we're drawing this graph here, I wouldn't have omitted M equal to 3. Yeah, will be between M equal to 2 and 3, and we can even calculate that, right? If you get the wavelength, and if we get the grating that was used for that, we could calculate that using that equation that you saw. The optically variable graph. So that's one of the applications, right? Yeah, here you go. Your credit card also has something like that. Optical variable graph. I'm not gonna ask about that. Okay. Yeah. Let's see what else we have. Gratings, dispersion and resolving power. Okay, so let's go for our break first. And now it's almost 11:25. And what I'm going to do, not going to cover this last section. Yeah, so let me just summarize what we did here. Sections covered. before you go into our break, 36.1, 36.2, 36.3, and 36.4, 36.5. Yeah, we're not going to do those two. Okay, we stop at 36.5. 11:25. Yeah, let's see, would the homework and the book problems be good? Yes. Yes, they would. And examples too. Don't forget the examples in the book, right? You study the examples as well. Study the examples in the book as well. What else did we do? We did here 35. Oh yeah, 35, we did everything, right? Light as a wave, via interference experiment, interference and double slit intensity, interference from thin film, 31.1 through 35.1 to 35.5. 35.1, 0.2, 0.3, 0.4, 0.5. And what did we do in 34? Image, yeah. Let's see, one more student coming here. $34. Going back here to the beginning of the class, right? Yeah, 1, 2. That would be for exam 2. And I'm gonna copy and paste so we can keep track of everything that we have done so far. Okay, exam 2. That should be for at least exam 3, right? So far, exam 3. But that will be exam 3 for next week. For tomorrow, tomorrow's exam is going to be just those 2 chapters. Exam 1, those chapters, right? And then 2 weeks from now, we're going to have our final. That's very crazy, isn't that? I prefer an 8-week course instead of a 5-week course. 10 weeks course would be better. 5-week course is too quick, too fast. But let's go ahead and have our break, as it is half an hour break, lunch break. 11:30 to 12 noon. Any more questions? So I see you in half an hour. Okay, so I forgot to record that, right? Let me just repeat what I did, right? So here you go. I found a better picture of you out there in the internet describing how grating projects break down the white light into different color components. What you see right in here is a white light source. What you see here is the grating, a transmission grating. And far away there in the wall, you see the 0 order maximum. That's a white light. All the colors are mixed up right here. But then as we move to the left and to the right, we see that the white light is broken down in their blue, green, and red color. That would be M equal to 0 here, M equal to 1 here, M equal to 2. M equal to -1, M equal to -2. This is This light source is a light source of continuous spectrum. You have you don't have a line spectrum here, but we have rather a continuous distribution of blue, green, and red colors. RGB, right? RGB, the main colors of the spectrum. If you mix up red, green, and blue, you can get whatever color you want, if you mix them up in a proper way. So that's a real live picture that you're seeing here, but we also have something slightly different, which is the case of the emissions of the hydrogen atom. If you get a bulb, if you put the hydrogen atoms inside the bulb and seal it, pass a voltage, apply a voltage to the terminals of the light source, the gas inside the bulb will start to emit light. That's the principle of the arc lamps. Arc lamps were the very first type of electrical light source invented by mankind, which was not the incandescent light bulb. No, incandescent light bulb was not the first light source, electrical light source. The first electrical light source was the arc lamp. So we came up with all sorts of arc lamps in the past, back in the 1800s, okay? We came up with arc lamps of hydrogen, arc lamps of helium, of neon, xenon, and they all had this type of spectral distribution, this line spectrum. This is the line spectrum for the hydrogen. And when you pass the light of a arc lamp, hydrogen arc lamp, you get something like that. A bright central maximum that is white in color, and then the colors of the spectrum of the lamp: violet, blue, green, red, right? Violet, blue, green, red, violet, blue, the green. We don't see the red here, but we do see the blue, the green, right? If you were to project these spectral lines in that picture, or that picture that you saw, you would have again, if you were to put a hydrogen lamp right here in place of this other light bulb, right, and pass the light from the hydrogen lamp through this transmission grating, you are going to get a bright spot here, and then those lines, right, with those colors, those 4 distinct colors and 4 distinct separation: violet, blue, green, and red for m equal to 1. Then violet, blue, green, and red, but it would be a line, it wouldn't be that thing, that broad distribution of colors that you see. Okay, so 2 types of different spectrum: continuous spectrum, light from the sun is a continuous spectrum, and then light from an arc lamp made of different of specific gases would have a line spectrum. Let me close that, and now it's time for our lab. There are 17 students. Any questions before we move forward? Okay, so going back to our syllabus, right? Lab 3 is going to be so-called experiment of standing waves, right? And let me take attendance first. Roster. Attendance lab. Six 28. Amy, are you there? Okay. Next is Alisa.
Here.
Thank you, Alisa. Ashley, Ty.
Here.
Next is Sartak Kamerkar. Good. Mary Shukorian. Next is Raymond Silverman. Good. Basilio Lopez.
Here, Professor.
Thank you. Joshua Mohan.
Here.
Thank you. Zaid. Okay, thank you, Zaid. Next is Kartika.
I'm here.
Thank you. Sydney.
Here.
Next is Sumana. Next is Kyriakos. Okay, Kyriakos, and everybody's here, right? Andy? Is Andy there? Okay, I'm gonna put a star here because I see Andy in my roster. Alex Hernandez. Good, thank you, Alex. Alexis Valley. Madrigal Valley.
Here.
And we have, oh, there's one more student, right? We have 17, okay. And the other student is Parth. Kenna, are you there? Parth, Kenna. Okay, good. Lab. Left. Okay, you do not have a group, Parth. Let me see how we're gonna do it. And (16), we have Andy 17, 18. Good. Now, do you know anybody here in the classroom, Parth? No? Nobody? Okay. Okay, who wants to have Parth in their group? You know, preferably any group other than group number 4, right? Because group number 4 already have 4 students. Can be group 1, 2, 3, or 5. Who needs help from Parth? Parth needs a home for the lab experiment for the rest of the semester. See. Okay, I think I'm gonna fit Parth himself. Okay, so what about group number 2? Okay, would you like to welcome Parth to your group? Raymond, Mary, and Sartak? Why not? Okay, good. Okay. Group 6 now. Group 6 he would be alone. Poor Parth, right? I'll put here on group number 2, and let's see. We're gonna join group number 2, Parth, and exchange information, contact information with your group members. You can do that through the chat message, or if you want something more private, you can go to Canvas and we'll sort that group number. Okay. Number and email me. Yeah, good. Here you go, Parth. You already have a Raymond email. And here are your group members, Parth. Sartak, Mary, Raymond, and you. Okay? And I'm going to provide you with a link to the group folder. Through Google Drive. Group number 2, copy link, And here's the group folder. Don't share this link with anyone else outside your group, okay? It's okay to share this link with the other group members, the other 3 students that are in your group. And what I'm going to do, I'm going to upload the data for lab number 3. Let me make sure everything looks good here first. This is a really neat experiment. I like to do it because it works very well. And then you can also see the formation of the standing waves. Okay, this one looks good. This one looks good too. Looks good. Hey, wait a minute, something wrong here. Spring is in parallel. No, it doesn't make any sense. Yeah, that's the wrong one. It's not the one I want. Let me get the other. Maybe it's the number 4. Why it says number 5 here? Huh. Something wrong here. Let's see. Okay, that's not the one either. Let's see. Not what I want. Standing wave 1 is standing wave 2, and then okay, that should be speed of this one. The one that we're seeing here is 5. Yeah, that's 5. So about this one. Okay, this one we already saw. For some reason, lab 4. Nope. Lab 5. Okay, must be this one here. This for some reason it's numbered number 5 here. Let's see number 6. Yeah, okay, good. For some reason misnumbered here, shouldn't be this misnumbered. Okay, good. So I will fix that. Okay, so that should be lab number 3. Okay, and I will have to relabel this one as something else. And now this become number 3. And let's go through that again. Make sure I'm not going to give you something that's not what it's supposed to be. Okay, here is mass of the string, length of the string, length of the vibration length of the string, the frequency, the mass, the mass density, and the acceleration of gravity. That's what it is, okay? And I'm going to go carefully through this experiment. We are going to good. Uh-oh, this thing is not supposed to be here. Yeah, it's not supposed to be here. Okay. Seems to be good. Looks good to me. Looks good. And this one looks good. Let me take it out. Can I have the link for the drive again? Yes. Your group number. Tell me which group you are, Alexis. Tell me your group number and I will get you the link. Don't forget to copy and paste it in a safe place, okay? So you don't miss it again. Group 5. Okay, let me upload this spreadsheet first, and then I'll give you the link. Group number 1. Let me take a look at this one here. Yeah, okay, good. Group number 1. Okay, you have your spreadsheet there. Group number 2, you have your spreadsheet there. Group number 3. I hope I put that in the group number 3, right? Yeah, I did. Group number 4 and group number 5. So Alexis needed link to your group folder. Make sure it works well, okay? It works correctly. And let's get the notes for the lab. We don't need that anymore. There will be 2 experiments on standing waves, okay? This one here, no, not the one I want. No, this one. No. Now let's take a look at the lab notes. standing wave. Okay, lab 3. Let's take, I'm gonna copy that and paste into your you know what? I'm gonna copy everything. Speed of sound 5. Again, double impedance, do the again double slit experiment. Microphone interferometer. Diffraction grating. That's what we have here. And yeah, where are the sig figs for the measurements? We're gonna get there. I'm putting everything in a single document, so you don't have to, I don't have to keep on copy and paste every time we meet, right? So those are the instructions for the labs, not just today's lab, but the other ones that are gonna come as well. That there are lab 1, lab number 3 is the standing waves 1, and lab number 4 standing waves 2. Here you go, standing waves 1. Good. Lab number 3. And okay, just a quick review. Before we go into this review, let me go there to YouTube and see how this standing wave experiment is performed, right? So you can see in real life standing wave experiment, YouTube. Okay. It's a really neat experiment. I like to perform that. It works well all the time. Okay. Let me raise the volume. I'm going to get this link here and paste into the notes as well. Check link in YouTube. Okay. Good.
Connected to what's called a wave driver. It's just a
Standing wave demo.
so we have
Okay, so let's see what we have here. We have a string here, and he put this black screen so the white string can, can be seen more easily. What you see right in here is this interesting device, okay? The thing is just like a speaker. It's a speaker that you can drive at different frequencies. This speaker works as the oscillator, okay? It's something that moves up and down at a given frequency, and you can adjust the frequency with this box that you see here. And this is a standard equipment that you see in any lab, any decent physics lab, okay? It's a device that you can adjust the frequency of vibration of this driver. We call it the driver. When he turns on, you're going to see it moving up and down. And the other end of the string is fixed somewhere here. We don't see it, but it's supposed to be fixed.
here's a frequency generator.
frequency generator. Like I said, frequency generator is available at any lab. Okay, so let me see. Lab doesn't match the lab research from the textbook. Are you referring to the lab manual, or Sartak? Okay, so let me check. Did you check we have 2 labs on standing waves, okay, Sartak? Check if the other description matches what's there in the spreadsheet. I presume that if the one that you're seeing doesn't match, maybe the other one should match, okay? And if you cannot get it, let me know again, and I will look for the lab manual, okay? Let's do this way. Anybody else is having any problems with the spreadsheet and the lab manual? Okay. So Sartak, let me know. Okay, so if you check the other experiment in the lab manual and see if it matches with the spreadsheet. If it doesn't match with the spreadsheet, then I'll look for my own lab manual here in my computer. From the supposed to be lab 5 from the manual. Yeah, okay. Yeah, the numbers are mixed up. You're right. I used to do another experiment for that. That's why. Okay, I presume that lab number 3 is the string, right? Lab number 4 is the speed of the sound. That's what it is. Okay, in my lab manual, I put that in that order, I presume. Lab number 3 was the spring, which is the Hooke's law, and then lab number 4 was the speed of the sound. That's what the confusion is all about. And now lab number 5 should be this experiment that we're doing today, and lab number 6 should be the next waves experiment, right? Right, Sartak? It's just a mix up in the number there. I used to do those lab 3s and 4s in the past, then I changed the order. So let's continue here, right? So here we go.
It's connected to what's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. Sends a wave down to this end, the wave reflects.
Thickest end.
Now, if I set it to just any old frequency,
okay, here you go. Do you see how it move up and down?
So
now it's faster, right? But at the beginning, it just is lower. See, it's lower now, and then he will increase the frequency just by adjusting the device.
Waves back and forth, but these waves are out of sync, if you like. They're not existing.
See, these waves are out of sync. Because they're out of sync, it's not forming a standing wave. It's not forming a standing wave. But there are some specific frequency for this length of the string, for this mass of the string. There is a specific frequency, not just one, but several, in which you can generate standing waves. Standing waves that are fundamental, 2 lobes, 3 lobes, and so on, okay?
Exhibiting consistently constructive or destructive.
Right now, it's not at the right frequency, okay? Right now, but it's close. Apparently, it's close.
But if I set it here.
Okay, he's getting there. See that? 2 lobes. 2 lobes, and he has the frequency adjusted here in this box. That's exactly how we performed the experiment in the classroom.
I have what's called a standing wave.
This is a standing wave.
The wave that's sent down and reflects.
This is not the fundamental mode, right? The fundamental mode is just a single lobe.
Constructively interferes with the next wave that comes down right at this point. Now the waves that reflect, that come down and reflect, destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it's still working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera.
Okay, so here's the high-speed camera. Unfortunately, we don't have that there at LA Harbor. So he just
So
slowed
this
down the
is
high-speed
called
camera.
the second harmonic. The second possibility for a standing wave for a string that's held at both ends. Because notice this is a node, this is a node, and the middle is a node.
Strictly speaking, okay, strictly speaking, this point here is not a node. Although he said that it is a node, it's not. It's not because that's where the point, that's a point where it is moving up and down, okay? So, but the node is close enough. The node, it looks like the node is right in here, a little bit to the right of the oscillator. Definitely the position of the oscillator cannot be a node because at the position of the oscillator, this string is moving up and down. But you can see it looks like I said before, the node is right in here, just to the right of the oscillator, okay?
3 nodes for this one. Now, like I said, second harmonic, what's the first one? The first one will be half this number, so 8.5.
And now he's adjusting the frequency again. The frequency of the fundamental mode is supposed to be half the frequency of that second harmonic. Okay, so that high-speed camera, right? We need one of those there at the Lake Harbor.
Basically the scenario of a jumper. Now,
That's the type of mode that we excite in the strings of a guitar, right? That's the type of mode that we excite in the string of a guitar. It's interesting that I have never been able to excite a second harmonic in the string of a guitar. I have never been able to do that. If you folks have been able, let me know. If you play music, right? Maybe there is some little trick here to excite the second harmonic in the strings of a guitar. Here in the lab, I have done that all the time with the generator.
like any of the other all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I can get the third harmonic. Well, 3 times 8.5, I can 25.5.
Okay, that's the third harmonic.
And there we go.
3 times the frequency of the
So
fundamental.
that's the third harmonic. How many wavelengths is this? Well, it's 1.5. 1.5 wavelengths. And it's easier to see in high speed. So check out this shot with the high speed camera and verify for yourself that it is 1.5 wavelengths.
Here you go. See here, this guy is moving up and down, so definitely it's not a
So
node.
again, third harmonic, 1.5 wavelengths. Well, let's go to the sixth harmonic. The sixth harmonic will just be double this frequency. So you go up to 50.
Oh, nice.
There we go.
1, 2, 3, 4, 5, 6 lobes.
And it's 6 times the fundamental frequency, which we measured in the beginning to be 8.5 hertz. So check this guy out. We have 1, 2, 3 wavelengths. And in the next video, the explanation video, we'll go through the calculations and the derivation.
Okay, so now that you have an idea how this experiment is performed, what he didn't show you, okay, he didn't show you something that I usually do in my labs, is that instead of tying the string to this stand, I actually put a weight at the end of the string, so I know exactly what is the tension in the string, right? If I put 1 kilogram mass attached to the end of the string, I know that the string, the tension in the string is going to be 10 newtons, okay? If I put 2 kilograms, it's going to be 20 newtons, and so on. That's what we usually do. And I can illustrate that for you, okay? It's all illustrated in my notes here. I'm gonna go, okay, that's the experimental procedure, okay? In my experiment, I use exactly what that guy was using. Use a Pasco device, but I didn't illustrate the Pasco device here. Use the oscillator. At LA Harbor, we use something else called the vibrating fork, but the vibrating fork is not as good as the Pasco oscillator. Okay, here you go. The string is deployed, is attached to the oscillator and deployed along a pulley. And we tie a mass to the end of the string, a hanging mass. mg is the tension applied to the string. Mass times acceleration of gravity. Okay, that's how simple like that. Mental is simple like that. But let's review the theory so you know what you're doing. Right? A wave is a disturbance that propagates in a medium. A medium can be string, air, solid metal, vacuum, etc. You can generate a wave in a string by moving string up and down with your hand or any other device. Okay. A wave has the same component that a source of vibration has. A vibrating source has an amplitude and a frequency. Okay, but once the vibrating source generates a wave is going to have its own amplitude that's not going to coincide with the amplitude of the oscillator. Okay, the amplitude of the wave is not necessarily the same as the amplitude of the oscillator. I'm going to put it here. The amplitude of the oscillator is not necessarily equal to the amplitude of the wave. But the frequency of the oscillator is going to be the same as the frequency of the wave. And the wavelengths. The oscillator doesn't have a wavelength. Okay, doesn't have a wavelength. There is an inverse relationship between the period and the frequency. And there is this relationship for the velocity of the wave, the speed of the wave, lambda over the period. What you see right in here is the genetic definition of the velocity. For each specific medium, you're going to have a second equation for the speed that's going to depend on the characteristics of the medium. Let's wait here for my computer to get out of this loop, this infinite loop, right? Every now and then it does that to me. Let's see. Hopefully I don't have to quit this guy. Oh, it's taking too long. Let me momentarily stop talking. I'm going to rewrite this equation. It should be lambda times the frequency. That's the generic definition of velocity. Every wave obeys this relationship for velocity. However, depending on the type of wave, we can rewrite this velocity in a different way, right? I mentioned that before. For the case of the electromagnetic wave in vacuum, okay, that's no extra credit. It's given by the inverse of the square root of epsilon naught mu naught. If the wave is not in the vacuum, then the above equation becomes something slightly different. Epsilon naught and mu naught are parameters that are applicable to the vacuum. Now, in this case, epsilon and mu is going to depend on those parameters are going to depend on the medium, whether it's glass, water, or something else. But we're not talking about electromagnetic waves here today. Today, we are talking about a wave in a string, right? And the wave in the string, not only we have this relation, but we also have this relation here, where F is the tension and mu is the linear mass density of the string. Linear mass density of the string is going to be the mass of the string divided by the total length of the string. And that's where we start with our table. See, okay, I don't want this one. I want the other one. This one, right? That's the one. Oh no, that's not the one. I'm looking at the wrong one here. Let's see, why is that? Ah. Okay, now I'm in the right place. Let's look here, lab number 8. Lab number 8, group number 8. Here you go. Okay. So we start by measuring the mass of the string and the total length of the string. Let's take a look at the resolution, right, of each of those devices. And so one, measure the mass of the string, right? And the resolution is going to be x dot 1, 2, 3, 4, 5 in kilograms, right? It's the same, is going to be the same scale that we used last time before. And then measure the length of the string. Measure the mass of the string with the scale, with the provided scale. Measure the length of the string with a meter stick. The meter stick has a resolution of 1 millimeter. Consequently, it's going to have 3 decimal places. Okay. And that's the one. Resolution up to the 5th decimal place, resolution up to the 3rd decimal place. Don't forget, that's the length of the string, that's the mass of the string. This L prime is something else. We're going to get there. The unit here for the mass, the unit here for the length. And then you have to fill up all the units here, right? Okay, so prove using dimensional analysis that above square root reduces to the unit of velocity. Are the sig figs for gravity still 2? No, the sig figs, the significant figures for the gravity you consider to have infinite number, okay? Keep that in mind. Yeah, whatever I don't, whatever is marked in red, you don't use as a, let me write that down here. Where is the gravity? Okay, I gotta put that in red, okay? Whatever is in red, you don't worry about the significant figures, and you consider to have, you know, isn't market. Yeah, that's right. So just supposed to be in red. That's right. Okay. Let me write that down. G is supposed to have an infinite number of significant figures. Okay. For every lab that we do, G is supposed to have this infinite number, unless we are calculating, unless we are determining G in the experiment. Yeah, that's the unit of G. Yeah. And let's go. Let's continue today with the description of the experiment. Not this one. Okay, so prove that this, what you see right in here is going to be units of meters per second, okay? Using dimensional analysis. And here's my proof. It's not difficult to do that. But keep that in mind. The tension in this specific case is going to be mg, okay? The mass is stretching this string and providing a tension that is equal to its weight. The L is upstairs because it was downstairs, right? Because it was dividing, it ended up being upstairs. So vibrating fork, vibrating source to produce a wave in the string of length L. Okay, length of the, oh, by the way, there's a difference between the string, the length of the string, right? That's the length of the string. And that's what you are going to end up measuring the mass of and measuring the total length. And then there is the length of the vibrating string. What's going to be vibrating is going to be this length here. This length is the one that's going to be vibrating. This one I call L prime. And you're measuring this L prime also with the meter stick. L prime is right in here. Okay. And the frequency of vibration that we are going to use in this experiment is 50 hertz. Okay. Once you get the mass of the string and the length, the total length of the string, you can get the linear mass density of the string. Okay. And go ahead, use the proper non-sequence figures. In order to find out the sequence figures here, you gotta get the sequence figures here and here. What's your raw data? Your raw data is this one here. Okay. This one is a result. This one was a previous result that we did for an experiment in physics 37, right? Then what are we going to do? What's the process? What is the procedure, right, for this experiment? I'm going to put everything in numbers. Gonna change. You should change too, because what you have here is the mode of vibration. Fundamental mode of vibration, second harmonic, third, fourth, fifth, sixth harmonic. N is an integer number. And what this M is? This M is that hanging mass that you are putting out there at the end. Okay? And you're going to measure the mass that you're putting there. Notice that the last column is the tension in the string, or the weight of the mass that you're hanging, M times G. Can we assume it's the same sig figure of mass above? For M, yes. Wait a minute. Yes, no, it's not the same sig figs. You gotta be careful with that. Okay, it's going to be the same number of decimal places, right? Here's going to have 5 decimal places, not necessarily 5 significant figures. Yeah, scales do that. That's right. And here you're going to have 5 decimal places too, not necessarily 5 significant figures. Okay, we are using the same scale for measuring those two masses. So what we do here, we are let's go back to our due to G being sig figure, so do so for MG to be the same. Yeah, that's right. MG will have the same number of significant figures as the M. Yeah. As the M, and G is considered to have an infinite number of significant figures in our experiment. See what I have here. Okay, so what are we doing here in this experiment? We are changing the tension, okay, to get the different modes of vibration. Okay, and I am providing with those masses, and I'm asking you, look, folks. I'm currently trying to increase the decimal value for the number on my chart, but that's for it goes. Yes. So how do we fix that? There's a way to fix that, right, Raymond? How do we fix that? I'm gonna illustrate that for you. Here you go. Here you go. I'm gonna illustrate that for you. See what happened to this number here? I shrunk too much the column, right? And then you have to spread it out a little bit more, okay? Okay, so the way we do this experiment is the following. First, I want the fundamental mode of vibration, right? And the frequency of vibration is this one, 50 hertz. Given this frequency, 50 hertz, find the mass to generate the fundamental mode of vibration. And the student did it. He found this one. Given the same frequency, we're not changing the frequency whatsoever. We're just changing the mode of vibration and finding the tension, right? The mass that will generate the tension that will reproduce two modes of vibration. That's what we're doing here. Make sense? Okay. Three nodes, three lobes, right? Not nodes, lobes. Three lobes will get to that. No, and the students, you know, they do that in the classroom, okay? So we're measuring the mass, and then we are measuring the wavelengths too. It's not difficult to measure the wavelengths, right? All you have to do is to measure the distance between every other node with the stick, with the meter stick. So let's write it down. Okay, vibrating fork, string of length L, length of the vibration is of this vibrating string is L prime, and what else we're measuring? Measure the wavelengths. Measure the wavelengths with the meter stick, right? Which is going to be also x dot xxx in meter. The vibration frequency of the vibrating fork, we use a strobe light. Okay, and I already gave you what's the vibrating frequency of the fork. In the case of LA Harbor, we do not have that Pasco oscillator that we can adjust the frequency, unfortunately, okay? In the case of LA Harbor, where I do this experiment, all we have is this vibrating fork that's set to a frequency of 50 hertz, unfortunately, okay? But you still can do the experiment. Okay, and here go all the raw data. Mass of on the string. Mass of the string, right? Mass of the hanging mass. L, total length of the string, vibrating length of the string, and the wavelength of the string. Okay, for a single lobe, the length of the vibrating string is going to be half of a wavelength. For two lobes, the length of the vibration string is going to be equal to the wavelengths, and so on. For n lobes of vibration, we have that. That's relationship, okay? And then What else? I'm doing the theory here, right? V equal lambda over T, lambda F. The frequency is going to be given by, oh, so not the frequency, sorry. The lambda is going to be replaced by this value here, which was obtained right here, right? But let's not forget, this is the genetic relation that came from here. And here is the specific relation for the speed of the wave in a string. Now, what are we going to plot, right? That's what I'm doing here. I'm going to show you what we're going to plot. I have to square both sides because I want to get a linear relation. This term is going to be squared. This term is also going to be squared. But when it's squared, that's the only thing that's left. Okay. And I'm going to call that my y-axis. And we are changing, the frequency is constant. The length of the vibrating string is going to be constant. The unit mass, the mass per unit length is constant. What is changing is the n. And that's going to be the one that we're going to plot on the x along the x-axis. That's the first thing that you're going to do. Okay? So plot, plot mg along the y-axis and 1n squared along the x-axis. Right here. That's your first graph that you're gonna get. And then your slope is supposed to be equal to, this value. 4L prime squared, frequency squared. So that's your first step. Plot mg along the y-axis. And 1 divided by n squared along the x-axis. If I do that on the spreadsheet, see that? Data, data, and data. Result and result, right? That's data, 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 and data. This frequency we get with strobe light. Data, data, data. Result. Result. And I'm going to plot those two here. Insert, chart, okay? See how nice of a straight line I get? And then I go ahead and add the trend line. Linear, display equation, blah, blah, blah. Do you care about sig figs in the axis for the graph? No. In the axis for the graphs, I don't care about the sig figs. Yeah, you shouldn't have that many sequence digits, right? That many decimal places in the axis, otherwise they're gonna crumble, right? Yeah, hard to read. Yeah, that's very difficult to read. Now, what I got here is 10.056. Let's see if we see that is my experimental result, and that's my theoretical result. 10.06, right? Only 1% difference. Only 1.4% difference. Okay. Good. So you can start working on that. What time is that? 1:10, right? Let's have a little break, right? Today I woke up with a sore throat. Huh. And I'm taking this warm tea so I can soothe my sore throat. It's working pretty well. So, and I need a break too, okay? So let's go for our break, and that's almost 1:10. Break. I'm gonna put 1:10 here. 1:10 to 1:25 p.m. Right? I'll see you in 15 minutes. Okay, so that's the drill, right? So for L prime square F square, let's make sure that this equation is correct. For H6 square, H6 is this one here. G6 square is this one here. L prime square, F prime square, F square. So we do get a good result. That was, in my case, it was only 1% difference. And then you gotta do what you have been doing all the time, right? So he go plot the graph. One, two, log the slope in the table, in the appropriate table. And check the percentage difference. Two, fill up the units. Work on the sig figs. Remember, I'm gonna remind you, right? Remember that the number of sig figs is not necessarily the same as the number of decimal places. And what else you have to do? But the graph, log in the value of R square, right? R square, find CL, confidence level. So those are the 6 tasks you have to do. Let's see how you're all doing. Roster here. $28 today, so he goes fifth meeting, right? Download. Let's make sure everybody downloaded. I need you to download the spreadsheet. Yes, okay, good. Okay, yes. Alisa, did you download the spreadsheet?
Yeah.
Okay, good. Ashley, you download
Yes.
this? Good. Sartak, did you download the spreadsheet? Yeah, good. Okay, so let's skip some of the students here. Let's see, Part, did you manage to download the spreadsheet? Yes, that's good. Okay, let's go for Zaid now. Did you download the spreadsheet, Zaid? Okay. Sumana, did you download the spreadsheet? Okay. Raymond, right? Yes, yeah, I was also able. Okay. And Sumana, right now it's Sumana. Is Sumana there? Not there. Okay, let me put a 0 here. Oh. Andy, were you able to download the spreadsheet? Are you Andy there? Okay. So a second star here for Andy. Let's go for Alexis. Did you download the spreadsheet?
Yes.
Okay, good. So the next step is to plot the graph, right? Let's see, let's go here. Mary, did you plot the graph?
I'm doing it right now.
You're getting it, working on that, right?
Yeah.
Okay, Basilio, did you plot the graph?
Yes.
Okay. Jeshwan, did you plot the graph?
Yes, Professor.
Okay, good. Let's go for Kartika. Did you plot the graph? I don't see Kartika here, huh? Okay, so let's see what would. Okay, okay. Thank you, Raymond. I'm gonna put it here. Say Kartika is not here. Okay, I'm gonna put a star here for Kartika. And Sydney, did you plot the graph?
Yes, I did.
Okay, good. Why did I put O here? Oh
I
no.
think you're looking at Sumana,
Yeah,
not me.
I put no.
Okay.
Yep. Sometimes you can be confusing. Okay, Sumana. Simona is not present, right? And we're gonna give Andy another opportunity. Hi, Andy, are you there? Okay, Andy is not answering. Let's go for Alex. Alex Hernandez. Did you plot the graph, Alex? Hello, Alex. Okay, Alex is not answering, and we have 15 students here. Okay, okay, so let's see who else. Some of you percentage are still working on the graph. Okay, good. Did you plot the graph? Yes, okay, good. So move on to the percentage difference now, right? Alisa, did you plot the graph?
Yeah, we're pretty much done with everything, I think.
Okay, so let me see you did the percentage difference, right?
Yeah.
Okay, what else? We did the units.
Mm-hmm.
Okay, and next one was sig figs.
Yeah.
The last one is the CL. You did everything? No questions? No
I don't
doubts?
think so.
Okay, so if you wanna go, you can go. So let's put here
Okay.
Dawn and the whole
Oh.
group. Just you.
Yeah.
The whole group,
Bar
right?
CL value.
The whole group.
Okay. Okay, so if you're done, you can go and 1, 2, 3. Next, Sartak. Did you plot the graph, Sartak? Did everything but still work? Okay, good. CL and sig figs, right? So CL and okay, sig figs working. Okay, good. And Mary, did you manage to finish the graph, Mary?
Yes.
Okay, so you're the same. So you did the percentage difference as well?
Yeah.
Okay, so we are working on the CL and sig figs, right? Let me put that CL and sig figs. I believe that applies to the whole group. Okay, if it doesn't apply to the whole group, let me know, please. Parts. How are you doing there, Part? Did you manage to plot the graph? I think so. So, okay, so what about the percentage difference? Did you get the percentage difference? Working on it, okay. Did you, in order to get the percentage difference, you have to get the regression equation plus the R square, right? Did you get the regression equation R square? Once you plot the graph, you'll be able to get the regression equation and R square. Did you do that? Okay, doing now. Okay, so here go regression equation and R square. So Parse is working on that. And now it's Basilio's time, right, Basilio? So did you
Yes.
get the regression equation and the R square?
No, not yet. Well, I could do that right now. I'm doing the significant figures right now.
Okay. So let me put here doing the sig fig. Oh, okay. My light went away. But that's okay because I have a no break here. Light returns. Isn't that nice to have a no break here?
Yeah.
Oh boy. I just discovered it recently. They sell this here in Brazil we call it no break. There in the United States we call it USB. Okay, it's a device that you connect to the electricity. It charges, has a battery in there, and then you connect your computer and everything to this device, right? To the USB. And if the light goes away, the USB can provide power for several hours for your computer and your modem, things like that. Okay. So it's man, it's a really good product to have around, especially if you're doing online teaching, right? Just as a
Yep.
reference for you folks. And Jeshuan, did you get the regression equation and this R square?
I'm done with everything, Professor.
Oh, everything? Okay. So I put here everything. If you want to go, you can go. And
Thank you.
Zaid, how are you doing there? Is Zaid there? I just need to find CL. Okay, good. So I will put like that and put working on CL. Let me see. Parse is working. Basil is working on the sig figs, right? Karsika, are you there, Karsika? Okay, so Karsika is not answering. Sydney?
Yes.
Okay, what did you do so far?
Right now I'm working on the CL.
CL, okay. Everything else you did, right? You did everything else.
Yes.
Okay, good. Sumana? Sumana is not here, right? Okay, I'll put the off here. Next. Kyriakos? Working on CL as well. Okay, good. So make sure you interface your group, okay? And working on CL, working here. Andy. Are you there, Andy? Andy is not answering, so another start here for Andy. Alex Hernandez. Alex, doesn't look like he's here. And Alexis Madrigal, how are you doing there, Alexis?
I just added the table, or sorry, the graph,
Okay.
and I got my y and r squared value, and
Okay.
I'm just working on the units right now, and I found the CL, so I'm pretty much done.
And what about the percentage difference? Did you get a good percentage difference there?
Yeah.
Okay. Okay. Okay, good. So good. Okay, Raymond is done, right, Raymond? Okay, so let me check here everything. 15 more minutes to go. Those students here are done. Okay, done with everything. Zaid, which group are you, Zaid? Group 3, right? Okay, good. Okay, done with CL, and then you're done with everything. Okay, you can go if you want. We can CL as well. So I'm going back to Basilio right now. Did you get the regression equation, the R square, Basilio?
Yes,
Okay, and the percentage difference, did you get you?
correct.
How much percent difference did you get there?
Let's see. I got, it was like a 0.1 something, 1.2.
Oh. Yeah, okay, 0.1 is more than,
Yeah,
yeah, that's,
I might have to redo it again. I noticed that if you accidentally like click power or like linear, if you,
Huh?
if you're picking on the graphs, it doesn't actually change your, what's it called? It doesn't actually switch your regression equation. I don't know if you noticed that.
Let me check. Let's
Cause
go.
it won't like, if you, so like, let's say if you like do the graph and
Uh-huh.
you, and you do the regression equation, but then you change it to power, it doesn't switch it.
Yes.
So I just noticed that.
Yeah, so here you go. I'm clicking linear, right? Display equation
Mhm.
chart, display R square, right?
Correct.
Now I'm gonna do on power, right? You said? That's what you said?
Mhm. Yes.
Oh, it did change the equation, see that?
Oh, maybe it's just my computer. It might just be hot. That's why. I don't know.
I don't know, maybe it's. I wonder if the R square was changed. Yeah, the R square must have changed as well. If I do polynomial, yeah, polynomial as well. Yeah, it works. Yeah. I don't know. Maybe it's your software, I do not know. So let's see. And Andy just returned here, and Andy with number 5. Okay, I need to. Okay, I'm giving you back here your attendance. Make sure you are there every time that I call you, Andy. And you're done, right, Andy? And that exceeded, yeah, okay, so. Yeah, so Andy is having a problem similar to what other students had, right? So let's go there. I am going to get the confidence level table. How many data points did you have there in the table, Andy, for this one, for this specific one? 8. Okay, here you go. 8.999, right? 0.999 falls outside here the table. Okay, so what can you, so if something like that happens, what do? Okay, you do the following. You know for a fact that the lower bound of the CL is going to be this one, right? That you know for a fact. You do not know if it's 1 minus 10 to minus 8. You do not know if it's 1 minus 10 to minus 9. Okay, all you know that whatever CL this one's going to fall on is going to be less than the maximum value of CL, that is 1. At the very extreme to the right of the table, you're going to have CL equal to 1, okay? That's all you can do. You're going to have a lower bound of 1 minus 10 to minus 7 and the upper bound of 1. That's all. So, Mr. Yeah, that's right. That's right. And you do the same thing when you have something similar, when you have something here to the right, right? If you get a CL R square of 0.4, right? 0.4, that's what's going to be, the highest one is going to be 0.95 and the lowest one is going to be 0. Okay, and now Andy, no, Alex, right? Alex Hernandez is here. Let's see, working, what are you working on? Did you plot the graph, Alex? Yes, okay. Did you get the regression equation? That goes for Alex Hernandez. Did you get the regression equation as well, Alex? Okay, Alex should be busy now. Let's see, let me try someone else. Someone is not here. Okay, and Kartika. That's Kartika here. No, Kartika left. Okay. Basilio, let's go back to Basilio. How are you doing there, Basilio? Did you finish the units?
Yes, I literally just finished it.
Okay, what about the sig figs?
Sig figs, yes.
Okay, CL.
Yes.
Okay, so you're done, right?
Yes.
Okay, good. If you wanna go, you can go. Let's see, how is Parse doing, Parse?
Have a great day, Professor.
You too. How are you doing there, Parse? Do you need any help? Okay, I don't hear from Parse. I'm gonna put a star here, and who else? Karsika is not here, Sumana is not here. Okay, and by the way, I gotta, when is it gonna be due, right? I'll tell you when it's due. So lab 1 due tomorrow. Lab 2 due Monday. Monday, July 3rd. And let's make lab 3 due on Wednesday, right? Oh yeah, this Tuesday is gonna be the 4th of July. Okay, so you don't have classes anyway. Lab 3 due July 5th. Any questions you have so far? Okay, let me go back to Parse. Parse, are you there? Parse Cannon. Okay, Alexis finished. Okay. Actually, Kyriakos. Okay, Kyriakos, did you finish? How do you do the CL? Okay, you're done. Okay, good. You can go if you want. Mary, do you need any help, Mary? Okay, Sydney, you're done, right? So let's put that here. Okay. Okay, so
Have a
Mary,
good day, Professor.
what's that?
See, I said have a good day.
Oh, thank you. You too. Have a
See you
good day.
tomorrow.
Tomorrow. And Mary, you're done. Okay, good. If you wanna go, you can go. Sartak, how are you doing there? Sartak, working on CL. Okay, good. So you finished sig figs, right? It's good. Make sure you work with your group members, right? Okay, we have 5 more minutes to go. Any questions? I have a quick question about our group 5 stick fix in lab 1, if possible. Yeah, go ahead. What's the question? Group 5. Group 5. Lab 1, group 5 here. Okay, I have it here. So what's the question? I'm not sure if I'm understanding it, but I put everything that involves time to be 2 digits behind the decimal. Yeah. I'm not sure if that's correct. Yeah, that's right. That's the correct one, because the timepiece the students were using was their cell phone, and the cell phone has a resolution of 100th of a second. And I'm not sure that's okay, since there are operations. Okay, it depends on the time that you're referring to. Okay, Andy. This one here, you will report up to the second decimal place. This one, all those 3 here, you report up to the second decimal place, okay? Make sense? Because those are actual measurements. The log, okay, the log, you don't report any significant digit. You leave the way it is, okay? Everything that's in red, you don't worry about sig figs, okay? Everything. Now, what about the T average and the T average here and this other square here of the T average? You gotta use, for this first T average, you have to use the summation rule, okay? You gotta use the summation rule for this one. Okay, so let's say this one, T1, T2, T3, you report with 2 decimal places, 1, 2. Okay, so that's what you're supposed to report. In order to get the T average, what do you do? In order to get the T average, first you're going to sum the T's, right? Sum the T's. So I'm going to sum here. Sum 1, 2, 3. Right? Now look what happens in this specific case. In this specific case, I'm still reporting after the second decimal place. But the moment that I sum, I end up with 4 significant digits instead of 3. Okay? Because I am summing. Now that you gain a significant digit, it doesn't happen all the time. Sometimes it happens. Now that you gain the significant digit, you're going to get the summation divided by 3. And then you report to the T average with 4 significant digits as well. Okay? That's how you do it. And then this T average depends on the number of significant figures of this one, depends on the number of significant figures of this. The number of significant figures of this one depends on the number of significant figures of this one. Okay? That's how it's done. Even if the result of the division only has 1 digit before the decimal. Which division are you referring to? Are you referring about this division here? Or this division here? 2617. Okay. Yeah, that's right. Yeah, you're dividing 4 significant digits by an integer number, right? This integer number has infinite number of significant digits. Then you report the result as 4 significant digits as well. Okay? So here should be format cell number 3 decimal places. You gain a significant digit. Yeah, that's right. It's based on the number of significant digits of the sum. That's how we calculate T average. So I'm not sure if that's more or less than. Okay, so how many are you talking about? What lab 1, 2, or 3? Which one? Which lab are you referring to, Sartai? Lab 3. Okay, so let me undo everything that I did now, and we go there. your group number 2. Let's get that. Group number 2, lab number 3, 2 o'clock. Let me stop the clock, the recording here.